working in many applied research in industry, not only in railways, and academia. He likes a lot the research, innovation, and research lead teaching, as you will see during the talk. And also is a very active member of our SAFEPROCESS technical committee and the mechatronics one. So thank you very much, Roger, for this nice presentation regarding fault tolerance in railways.
Thank you. Yeah, I haven't been a professor for 25 years, actually, but doing research for more than 25 years. So good morning. Thank you very much, Chairman. Thanks for the organisers for inviting me, and thanks mostly to you guys for getting up so early on a Thursday morning. For my part, I had no trouble getting here early because I was feeling a little bit nervous, so I woke up nice and early. I hope that by the time we get to the end in 40 or 50 minutes time of the talk that you'll feel it was worth getting in early. So I wanted to tell you first a little bit about me. So I'm part of the School of Engineering at University of Birmingham, and I'm also on the research side involved very much in the Railway Centre. Birmingham University has a really beautiful campus. It's located right in the middle of the UK. You could be forgiven looking at my map for thinking it's the biggest city in the UK. It's actually the second city of the UK. But it'd be nice to see some of you guys in the UK and in Birmingham if you ever want to come drop me a line. We have a good university, about 4,000 academics and 34,000 students, so quite a big university for the UK. A bit more about my background. So I'm an engineer, so I studied engineering, mechatronics as an undergraduate and MSc, and I got hooked into the magic of control systems engineering. So I spent 3 years doing a PhD in control systems engineering, and I've been stuck with that ever since, really. So I worked for 7 years for Alstom within the UK as a research engineer, and then I moved to Loughborough University for most of my academic career, and 6 years ago, 2018, moved to Birmingham for a change, and partly because my research was going more towards railways, and we have one of the biggest railway research centres in Europe. So on the professional side, a little bit more context where I'm coming from. So the things that I'm interested in, it's control systems science and maths, really, applied to solve engineering problems. So I like the fact that you can use these mathematical models, sometimes based on physics, sometimes based on data that we've collected. You can use these models as part of the design process to design mechatronic systems, the grey box up there, which is kind of the topic that we're mostly talking about today. That's at the centre of it. But you can also design fault-tolerant control systems and fault detection systems, condition monitoring systems, and I suppose where it started for me, feedback control loops that can optimize in real time the performance of our engineering systems. So that's kind of the background. The beauty of this, I think why it's kept me for so long in my career interested and engaged, is that you can apply it to all sorts of things. So everything on this picture is things that I've been applying the kind of tools and the maths that I've just mentioned to over my career with a whole bunch of students doing a lot of the work, to be honest. There's one thing on here that I have not put any automation or monitoring or any of the tools onto, and for those of you with a really good eyesight, if you can spot that, I'd encourage you in one of the coffee breaks, either later today or tomorrow, to come and have a chat with me and tell me which one you think it is. So a little challenge. So that's about me and the context, and now let's get on with the talk. So it's about a new approach to railway track switches. Some of you might know a little bit about rail, some not. So I'm going to introduce a little more about what those things are and what the problem is. I expect some of you might have been in this situation or recognize this situation. So a lot of people stood on a platform looking pretty somewhere between miserable and puzzled and going, where's the train? something I experience a lot on my commuting. Quite often, the trains can be delayed, and around about 20% of those delays in the UK, and similar figures in most places with commuter railways, 20% is down to things that we call railway points or railway track switches. These devices are causing 20% of the delays. In the UK, that means that Network Rail, who operate most of the UK's railways, are paying £30 million a year in compensation to the companies whose trains are delayed. So these things are quite a big cost. It gets worse because they occupy about 5% of the space on the railway, 5% of the infrastructure is track switches, approximately. But 5 times that, 25%, a quarter of the maintenance budget is spent on inspecting and maintaining those bits of the railway. So it's costing the railway industry a fortune, and the figures are for the UK, but we have some figures for other parts of the world. They're similar. So this project I'm going to tell you about, I'm hopefully going to take you a little bit on an adventure that I've been travelling on, which is going to provide a way to reduce those costs on the right-hand side and set all the trains, or maybe most of them would be a good start, to on time. And then we'll have, instead of lots of puzzled and miserable faces, lots of smiley faces. I thought I should show you some smiley faces at this time in the morning, because apparently when you look at smiley faces, it makes you smile. Hope so. So the journey started for me in 2011 with this project. So I've got quite a lot to cover, as you can imagine. But it started with this fundamental research question and some funding to do some fundamental research around railways. And the question was, could a fundamental rethink of railway track switching improve capacity and improve reliability at the system level and the availability of the nodes? Actually, nodes include stations and other things, but for my part of the question, it was track switches. So we set out on this journey, and I'm going to take you through some of the interesting bits, some of the bits that I thought were more relevant to the SAFEPROCESS community on that journey. So I'm going to tell you more about track switches and what they are. Some of you may already know. You have to bear with me if you do for a few minutes. So introduce the problem, talk about how we went about redesigning the track switch and how we then developed that as a lab demonstration, some full-scale demonstrations. We're going to talk a little bit about the fault-tolerant control side, the simulation side, and then where we are now, because unfortunately I can't tell you it's all done. The research part is done, but talk a little bit about what the next steps might be, try and draw some conclusions out of this all, and then coffee. Oh, questions, and then coffee. So the system, the railway track switch, is a device that allows trains to change route. So the bit that I draw your attention to is here, where we're moving these long plane down points, as they're sometimes called, or switch blades. They're being bent from one position to the other, and when they're in this position, the trains go straight through, and if you switch them the other way, couldn't make the animation work, but the train turns off and comes out the bottom of the picture. It takes the turnout route, as the railway people would say. So in the railways, we've been doing this for a couple of hundred years, slightly more than a couple of hundred years. And if you went back maybe 100 years, even 50 years ago, you'd have found this being done by people in signal boxes, pulling levers, and then through some crank mechanisms and cables and pulleys, this would be actuating some track switches somewhere in the reasonably near vicinity to the signal boxes. And this was still the case in some places even 40 or 50 years ago in the UK. There's some still on heritage railways that you can look at. The more modern ones, so around about 50 years, maybe slightly longer ago, we're starting to replace these, and most in the UK have now been replaced with electrical or hydraulic actuators sat at the side of the track, or sometimes in the middle of the track. So in this case, this system here is connected back to the signaling system electrically and electronically. And it's using a motor to drive the switch. So if we look inside, they don't all look, this isn't as old as it looks. They go rusty quite quick out there. So they look quite old and worn a lot quicker. So most of the network in the UK, more than half, has machines like this one on it. And if we look inside it, when it was shiny and new, we've got a graphic that kind of shows that. We've got a motor at the top, usually quite old motor technology, DC motor, driving through a gearbox and then into a complicated mechanism that has to, from that motor, drive an actuator which moves the switch blades left and right. But there's also a need to do locking. So as part of this mechanism, about halfway down and then coming down into the bottom, there's a complex device that translates the motion of the actuation that comes out of the gearbox into a linear moving, a locking pin in and out. So when the switch blades have been moved across, they get locked. And then they unlock next time and move back across. And then at the bottom, here we've got detection. So there's rods that are connected down here at what we call the toe, the very ends of the points. And they're there to detect whether the switch is over on the one side or all the way over on the other side. In between, we've no idea where it is with this kind of technology. And in here, lots of mechanical relay-based logic and contactors. So quite a complex machine. Most of them, there's a variety of different ways. Sometimes they're sat in the middle of the track, sometimes they're to one side. But most of them, when you take the lid off, they've all got to do these functions, and they look similar, like a bit like a complex analog watch, a wind-up watch. And in terms of in operation, here's one. It's not the best video clip, but it's the best video clip that I could find. So it's got to unlock, move across, lock, and detect, and then tell the signaling system that it has locked and detected, so it's safe for trains to come. The catch is, because it's safety critical, a single fault in any one of those elements causes the signaling systems to stop the trains. And that's why quite a lot of trains, when these things go wrong, quite a lot of trains are delayed. And it gets worse because to try and avoid these faults happening and stopping trains, we're spending a lot of money on inspection, just going to check it all looks okay, the tolerance is right for those sensing connecting rods. Did someone step on the rod and bend it and it's now out of calibration? All of that stuff costs money as well. So we're trying to do that in rail to avoid it. So that's the problem, yeah? So on to what can we do about that? Redesigning the track switch system to include redundancy. So my idea was, well, aircraft and other industries use redundant systems to avoid these single faults causing issues, shall we say. So can we do that in rail? And in the beginning, we started looking at fairly simple redundancy that we could add in to the existing switches. So in 2011, we're thinking about that, and we're doing some reliability calcs, and we presented a nice paper, I think it was a nice paper, at SAFEPROCESS in Mexico, 2012, looking at different configurations of parallel actuation, some parallel locking, the detection, including creating extra switches, so making the railway more complicated so there were ways around the bits that have failed. And not surprisingly, the maths comes out and tells you that, yeah, you can improve the reliability. But it's quite a large cost, particularly if you have to put in more switches and things. And so in the paper, I think we evaluated 7 different concepts and said, okay, we could do this, but probably it's not the way. And we had a bit of thinking, and we went back more to the original idea, which was let's rethink the thing from the beginning. What could we do? And so to do that, it took, well, it was a couple of years that this process evolved. So we had to get the stakeholders in the room. So we didn't know a lot about railway track switches, probably less than most of you at the beginning of the talk, hopefully about what you know now. So we got the industry stakeholders in the room and we started asking them, what are the requirements? Well, the Network Rail requirement document has something like 2,500 lines, and it's a recipe for making a track switch like the current ones. So we said, we don't want those, we want the basic requirements. And the basic requirements are probably two that come straight to mind when I'm looking at all of you. The first one is to allow the trains to change route. And the second one is to allow them to do that safely, so keep them on the track whilst they're changing route. So that's all we have to do. So we started thinking, how can we do that in a different way? And we looked at other industries. I mentioned the aerospace industry, the nuclear industry. What do they do in these safety critical scenarios, and some other industries? And we also just asked everyone to throw in their ideas. So we did quite a few workshops and we got sticky notes and stuck them up on the boards. It was before the electronic sticky notes really took off. So we're sticking the sticky notes everywhere. We had hundreds of ideas by the time we finished. And then we went through each one of those and put it in the could be good pile or the probably not so good pile. And then when we had, I think, about 20, we used this process up here with a Pew matrix, and we went through and we ranked them against criteria that we'd agreed with the stakeholder group. And eventually we got down to a handful of quite good ones, did it more thoroughly again, and got down to two ideas that I'm going to talk about next. So the two key ideas were to introduce a system with passive locking so that we could have multiple actuator bearers. So not just one machine that does the moving, but two or three. In fact, we thought three. So to do that, you need a different way of doing the locking, because if the system has three locks and one of them fails in a locked position, nothing's moving. So passive locking comes into it. And then the other part, the other idea, in some ways unrelated, but kind of linked quite nicely with the first idea, was to use a stub switch arrangement. So to change the layout of the switch, which you need to interlock the rails, and I'll show you a bit more about that in a minute. It allows you to have more than two routes out, potentially, so it could be quite good in some situations, in stations, maybe, in the entrance to stations. And you could do away with those long, plain down point blades that, if you ever see anyone making those, at least our local manufacturer in the UK, they have a big machine tool that's doing the machining, and the end of the switch rail is stuck out across their car park, sticking out the door, and they're planing this thing down. So no need for that with this new idea. How do the two bits work? So the passively locked actuator bearer, when it's down, like it is in the diagram now, those lugs with the red dots block it so that it can't move sideways. And to actuate it, you lift it, move it across, and lock it again. The advantage of this is because those brown rails are fastened to the grey part that's being lifted, if you grab the rails, you can lift it. So if we put two or three of these in parallel, when one fails to operate, the others can unlock the one or the two that are not working. And then the stub ends of this joint, what might they look like? Well, something a bit like this. In fact, I've got some photos later of some models of some real ones. So they're interlocked. The little gap here is for expansion, because steel rails expand and contract. So some of the first ideas we had about what this might look like would actually turn out to be a disaster in that sense. This one looks like the expansion joints. It looks to the wheel of the train like the expansion joints that we already have on the railway. So there's some, hopefully, some attraction to the industry for using that. Put those together and you get something like this. So after 2 years, we'd got some ideas that we thought had some scope and a little animation. And the challenge that we had at that stage actually was that industry advisors were saying, to get someone to pick this up, you can't tell anyone how it works. So we weren't showing people the animation at that point because they said, you've got to patent this, otherwise no company will invest the money that's needed to get you to a product. So we spent some time patenting it, and I spent some time giving talks where when we got to the how it works bit, I'd just have a skull and crossbones and say, I'm sorry, I can't tell you. Once the patents are published, we'll explain it. So luckily, we can explain it these days. There's a load of benefits. If you do this repoint type approach, there's a load of benefits, and the list goes on depending on where you put them, potentially. But I think the main ones, the take-homes for me that I'd like to leave with you guys about this bit is the passive locking bit was a real thing that unlocked the rest of it for us. It allows you to have redundancy in the actuation such that you can tolerate the faults. So then you get the reliability improvement for the system, and we can tolerate failures now so that when the system fails, we don't have to get the maintenance team into the van and rush out into the countryside or wherever it may be to fix the fault in real time. We can afford to go out and fix it or repair it or check it in our own time, because we know that one of the systems, the subsystems, has failed, but the two remaining ones are still doing the job. So we've got a window where trains are still running and it's all good. So I think they're the key takeaways for me. I suppose that's more from an academic perspective than an industry one. So we're at that point after a couple of years, and some people are saying, well, would it really work? So we built, 2 years later, we had this video of a system working in a lab. So right at the top, starting at the top of the picture, you've got 3 routes out, and then coming forward, you've got the rails. It's a scaled down railway. It's about 1/3 the size of a full gauge. You've got the rails that are moving on this thing that we not very imaginatively called a hopper at that time, the top surface of the actuator. A lot of it's made of plastic. We made it of whatever we could make the bits of. So some bits are kind of industrial and some bits are toy. And the Dexian that's used to hold it all together is really for making shelving units out of. So we got this in the lab. We marked out on the floor where the 2 redundant ones would be because we hadn't got enough money to make 3 of them, which is a shame. But it helped us capture the imagination of the industry. So we got the guys into the labs, and various people who came would go away saying, oh, this seems like a completely new way of doing things. We like it. So, that was good. One of the interesting things that we came up on at that time was about sensor faults. Yeah, so a little diversion into sensor faults, because quite a few talks that I've seen already are about that this week. So what happens if a sensor fails in a closed loop system? Because in this system we are operating in closed loop. Well, we wrote a paper about that which was presented in 2018 in Warsaw. Not the first thing on this subject that I've done, but Precious, who did that work, was applying the approach to our actuator system in the lab. So we got the motor on the left-hand side as you look at it, and we're monitoring the current and velocity, or we got sensors for current and velocity, and we also are sensing the position of the thing that I've called the rack. So it's a rack and pinion type design, so we need to know where the cams are. The closest to that we could get in this setup was to measure the rack linear position. And that's what we're interested in ultimately, because it is related mechanically to the position of these switch blades. So the control loops, they're not very complicated. 3 PI controllers in a nested loop with the current, the velocity, and the position. And what would happen if one of these had a fault was what the topic of that paper was. And it's quite interesting. And I've seen this on a few practical systems we've applied control to. If you put a fault into a real system, In the simulations that some colleagues have talked about, you can see that it goes wrong. But what really happens when it goes wrong? So just to show you why this is important. So it's running with a very slow controller because Precious was terrified of breaking the thing. And it just froze the hopper because we know that that's detachable from the rest of it so that the redundancy works with the other actuators. When you switch the velocity sensor, you just flick a switch and disconnect it, so it's like the wire's been chewed free by a rat maybe, or just become a faulty contact. You get a floating constant voltage. You might think that it probably, because of the other loops, wouldn't do too much harm, but actually it goes unstable and it froze the thing. So if that were a real track switch, we've probably done some damage. So it's quite important to do the fault-tolerant control. In the paper we explain we used a bank of observers, generate one for each sensor, generate some residuals. You get unique identification of the different sensor faults. You can also produce estimates of the missing sensor from one of the observers where it's still working. So the little detection bit up there, well, takes the detection signal and decides whether to pass through the real sensor signal or a software-based version from your observer. And then, of course, the video of it working isn't very interesting because when you disconnect the sensor, it just works. And actually, that's the beauty of control engineering for so many things, isn't it? It's hidden, and you don't notice it if it's working properly. So that was where we went to with that. And toward the end of that, we had filed the patents, thankfully. So we were able to tell people about this is how it works, and we were able to take people into the lab and show them this. And that enabled us to get the industry in the UK quite excited, as excited as railway people get. And we got some funding to make a full-scale demo of the system. So I'm going to talk a little bit about the simulation model, because we only had enough money to build this thing probably once, so we couldn't get it wrong. So we're going to rely on simulation first. And then they also said, we want you to apply your clever new lifting system to a conventional switch. We don't want these two innovations both at the same time. So let's have a look at that. So this was a project that we planned out. It's quite complicated. The most complicated thing probably I'd done as a researcher at that time. So it was going to take 2.5 years, and we had partners Progress Rail make switch panels, so they were going to help with that. DEG is a signaling company, so we needed to interface to the signaling system, our stuff. And RC Designs is a small outfit that designs some of the mechanical stuff, so AutoCAD experts, if you like. So they're doing some of the practical stuff on that side. At that time, I was at Loughborough University, and my team, 4 or 5 of us, I think, at that time, we were going through the modeling process, designing the overall system, doing the integration, the testing, and I suppose all of the exciting bits, leaving the mechanical specialists to do their bit and the electrical signaling people to do the signaling logic and so on. So that was the sort of time scale, and we're going to build it up, you know, one bit at a time, 1 bearer, 2 bearers in the lab, and so on. So let's have a look at that. A key thing here, this is a mechatronics project, really, for me. Though a lot of the colleagues that I go to the mechatronics conference, and they're talking about micro machines and mechatronics on a very small scale. This is the same sort of stuff, it's just bigger, yeah? You can't make it out of a piece of silicon. So we're going to design this system. It's going to be a conventional switch with the long switch blades that I'm not so keen on, but there you go. And we're going to have 3 actuators, the yellow ones. We got the different elements on there in the different colors, and in this talk I'm just going to summarize a little bit about the design of the actuator bearers, how that works, a little bit about the control system, and then show you the switch panel that we've made. So one of the first things is, okay, we had one in the lab. We had a lot of debates about how to make that in the early stages. So we're going to do this for real now. How do we do it? Do we use the same system with a motor and an actuator rod that we had in the lab? Do we maybe have 2 motors, one at each side, driving onto the cams directly? Or a third way would be to have some belts. And actually we came up with 5 or 6 different ways of doing this to go from an initial input to a mechanical motion of an arc. Yeah? There's the hydraulic options as well. So just to simplify this so we're not here all day, I've just listed 3 and, you know, a little question. Which one? A, B, or C? Actually, we had more choices. And we had to find a way to make that choice. Again, you can tell me your favorite one over coffee, if you like. The things that we were asked to consider by our stakeholders in that second project. Reliability, obviously, they care about that. Maintainability, it has to be maintainable. Hadn't really thought too much about that. How do you design this thing so people can access it and maintain it? Pretty tricky, actually. What about the initial cost? I don't know, this is like a crazy idea that we've had. How much will it cost? We've got to think about that. Can it be made? How easy is it to install? Can it be retrofit? And then the last one, which I've put an exclamation mark, because it seems absurd, really, but in some people's minds was the most important one, is it acceptable to the railway industry? I don't know quite how we judge that. I would have thought it'd be by the other 4, 5, 6 even criteria. But that was something that they wanted on the list. So we took all of those, and I've sort of simplified it a little bit, but we ranked them using a Pew matrix approach. Again, this is something I was taught, I think, as an MSc student, and I use it every time I have to make decisions. It's a great way of tracking your decision-making process and just explaining to someone who comes and asks you, why did you pick that one? Because it's a disastrous idea in the end, maybe. And you can say, well, we did do a proper process. Hopefully this isn't disastrous. We picked, in the end, the double motors one. I was partly pleased with that, actually, because it's the most mechatronic of the 3. We're not putting too many mechanical interconnections in there. So we go into like a switch-by-wire solution. So we got that. Okay, how big do these motors need to be? How do we make the mechanism? How do we make it take the load of the trains? All of that stuff had to be thought about. So we got the motors there and the cams that we eventually converged towards, and then the system that allows you to mount the rails on it comes in. We go through that process to design all that, and we had similar design challenges and choices. Where are we putting the sensors? They're built into this mechanism as well. And in the end, it's going to look something like this, with the locking blocks sort of here. There's another one here, stopping the lateral movement when it's in the down position. And how to pick these motors and how to size all this stuff. So there were 2 main simulation things that we were doing in our team. One was around the dynamics of bending the switch blades. 1 or 2 people told me it's not possible to bend a piece of rail in the vertical direction, which of course is nonsense. But anyway, the simulation confirmed it is possible, the static and dynamic simulation. So we build this simulation, and it allows us to integrate models of motors and control systems with bending a track switch. The other simulation that I'm not going to talk too much about today, but it is important, is about what the train experience is. So there's some papers that we've written, and there's loads of people in the railway community doing this, where they're simulating trains running down tracks and looking what happens as they go over joints onto bridges and through track switches and this kind of thing. So we've got to look at that and work out, does what we propose make it more uncomfortable for the passengers? Could be a bit inconvenient. Derail trains, that would be very unacceptable, that's the word. So in terms of this one, because it's closest to my world of interest and hopefully yours, what we had to do. So we used a package called Abacus, which is a 3D sort of design package to generate the rail bending models. And we export that into another package called SIMPAC, which is from Dassault Systems, and that allows us to model the complete track switch as a lot of connected free bodies. In parallel, we're building actuator models and control models in MATLAB and Simulink, and then we're putting it all together in this co-simulation. And we're using that to size the components. So we can put different gearboxes, different motors in, and see which ones work, so that hopefully we buy the right one. And what we had done in the first part of the work, with the work in the lab, is verified some of these models. So I'll just show you some results that we got from that. So for the electromechanical side, we were confident that the models we'd made worked because we tested them on the electromechanical system in the lab, and we found that the model predicted more or less the behavior that we saw in the real system with some confidence of more than 90%. So that was reassuring. So we used that in the design process, and eventually designed a model that in the Simulink front end looked a bit like this. So we had the finite element model of the rail bending and the actuators and sensors. We had the motor controller in there. We had some feedback loops that are actually hidden inside this part. And then we got from the various bearers 6 signals that are going into the detection system. And that's all interfaced out to the signaling to tell people it's safe for trains to come or not, and at the other end to take the commands to move the switch or not. The output from the SIMPAC thing, just for interest, I mean, this one's running with just 2 actuator bearers. This was the video that I found. It was easier when we made this one because to run this simulation is taking like half a day for 10 seconds or so. So we later improved that by pulling some more parts of the model into Simulink that was a bit faster. So you can model it, check it's all working, check that you've specified the right motors and things, and then buy it all and build it. Oh, design the control system. So just a thing to point out, the control system, the design of that, they might be frightened, my second year undergrads, but this is basically stuff that I teach the second year how to do. Only one loop at a time. So it's quite a simple design process. And we can test that in simulation. Then we start to build it in the lab, and you can see we've got a yellow actuator bearer. Railway people like yellow. If we zoom in on one end, we're just checking that the controllers on the 2 cams are making them go between plus or minus 180 degrees in synchronization, because we don't want to put it all together and find they go in different directions and break something. So we test that in the lab. There's a zoomed in version once we put the hopper part, the lifting part on top, and we make 3 more of those and test them in the lab. And then we go to Progress Rail, who've made us a nice switch panel, and they help us, because they're heavy, to install them underneath there. In the meantime, colleagues have been writing some LabVIEW code, and we're using a LabVIEW compact Rio system to implement the control logic and collect data, because we're still engineers and researchers, so we want data from this system as much as we want a nice video. And also a front end to show people what's going on with each of the 3 actuator bearers and the 2 motors in each. So we've got 6 motors that are all moving cams and systems, so we want to be able to look at that. And we find, perhaps not surprisingly, that you can bend rails vertically and laterally. And it all works quite nicely. We then go to the Great Central Railway, and this is a heritage railway, which is why there's a lot of grass on this siding. And with their help, they took some money from us to host us, but they did help us a lot in terms of digging up most of that track switch. And we put our switch panel on a truck and brought it from Nottingham to Leicestershire and lowered it into place in that siding. And it's the newest bit of kit that they've got there, albeit we've taken our actuators away now. And you can see the 3 actuator bearers in place there. I've called them 1, 2, and 3, not very imaginative. And A is the A side, the motor's on that side, the B motors are on the other side. These are there for some graphs I'll show you in a minute. We got the line side cabinet, which is a special railway certified line side cabinet, but with all of our control engineering gadgets in it. So at the top, you've got relays that mimic the behavior. The relays are mimicking the behavior of those mechanical contactors in the current switches so that we can interface to the same switching, the same signaling system that a conventional switch would. And then we got the 6 motor drives, a bit overkill to be honest, but it's a research project. So again, we want access to everything. And the MyRio and the laptop's simply there to enable us to tell it to switch because there isn't a signaling system at this Great Central Railway. It's a guy with a flag. So then it turns out, again, it works. So this was pretty cool. We drove some trains. The track didn't go very far, so you couldn't go fast over it, but we drove some trains over it. Not surprisingly, it worked as the simulations predicted in terms of the movement and in terms of not derailing the trains. So that was all good. And we had some posh events and showed people it and so on. We also collected the data and we went back to the lab and we looked at it. And this one's showing actuator number 3, so that's the first one furthest back down the switch. And the 2 motors in there, in terms of the cam positions, were matching up at the top perfectly. That's great. The velocities were matching up and the currents were pretty similar. That's all good. Then when we looked at motors A in all 3 of them, again, they were synchronized in terms of the motor and the cam positions. The velocities were very similar, but one of them was quite noisy, and we did eventually figure that out and fix that. And then the currents, we found that motor 2A wasn't doing any work at all. In fact, the second bearer in the middle was just moving itself. The other 2 were doing all the work. So even though the simulation model predicted they would share the load, share the job, the real actuators were not identical and they weren't sharing the work. So we've done some work on a load sharing scheme that takes account of that and tries to share things out. I don't know if you need that in practice or not. In the long run, it'd be nice. Make a nice paper anyway when we get it fully written up. At that stage, we thought we've cracked it, you know, and then the industry said, but we want the switch panel with the interconnected blades. Don't want these long blades after all. So the next bit of work was to do the whole thing again, but for a switch panel, and it's quicker, this version. It's going to look a bit like this, and when you actuate it, you see it move across like that. So it's a stub switch, but with 2 routes, so it kind of looks like it fits into the same space that the old style switch would fit in. And unfortunately, as usual, there wasn't quite enough money, so we were only going to build a real part of the bit in the red box. So I'll show you some of that. So some time passed, and we repeated all the design steps, did hazard identification workshops and all kinds of things like this. And then we had a design eventually, some more Pew matrices. We've got a nice, this time grey actuator bearer. Looks a bit cooler in grey, I think. Some slightly different motor and drive systems to do the lifting and moving. Some assistance to test out that all the blades move properly. Some people to design and implement, again, the controllers and everything, and same old modeling process to go through. And eventually we assembled the whole thing. And to cut a long story short, after about 3 years, it looks like this in the lab. So you have to imagine the other 2 in front that are giving the redundancy, because, again, not enough money to make 3 of them. But I'm confident that bit works. If you use your imagination, you can see part of what the next step might be. I'll let it just switch back. Leave it with the trains going right. It's not going to do it. Oh, yeah, there we go. Okay, so what's next? So we think we are at about TRL 5. I can confidently say that. Sometimes I'm pushed to say we're at TRL level 6, because that sometimes unlocks some other funding. But I don't think we have a prototype system. I think we've still got a couple of concept demonstrators, really. One was tested in a rail environment, but it wasn't designed to be manufacturable and maintainable and all of those good things. Not for me. So we've got to somehow clear this last bit of the gap. And the estimates for how much that might cost vary from about 2 million quid, I was thinking. Someone from industry told me it might be 6. So quite a bit of money, but the savings are way bigger than that, okay? And how to do that, I mean, at this stage, I'm getting a bit worn out because, you know, make one more track switch for us. I can't do that anymore. The research is finished. This guy who I use, one of my PhD graduates, he's been working on the repoint for a year or so, helping to commission that actuator in the lab, and he's interested in starting a small business. So he's got involved with this funding from the UK government to do a thing called iCure, which is about commercialising university research, and maybe holidays as well. So he's travelled the world for 3 months talking to all of the different industry players, actually just 8 countries, but it looks like the world on this map. He's travelled around and he's talked to over 100, maybe 150 different stakeholders from different railway industries and operators. And this was about validating the market. Do other countries have this problem? Yes, the answer was. And he's quantified some of that, and he's come up with some plans, and I should whiz through this. So our idea is we engage with the partners, because we don't want to be manufacturing any more switch machines, or, you know, that's not a thing universities really should be doing. We had to do it, but we don't want to keep doing that. So we want some companies to come in and work with us now. And the discovery stages, I show them a presentation a bit shorter, but a bit like this, no technical detail, some business cases, and they go, we like it. So we sign some NDAs and we share some more information with them about the nitty-gritty of how it all works. Then we get to evaluation, and then in somewhere between 3 and 5 years, depending on your optimism, we may be able to launch a product. So this is the plan that he's developed, and he's a really enthusiastic guy, and it's great to have someone on the team who isn't getting a bit jaded. In some ways, I'm a bit jaded with it. It's been a long journey so far. So we're going to build a collaboration proposal. We've got 2 routes that we're pitching. So if someone has all of the elements to do most of it, then the top route, our involvement is really as kind of consultants and guiding the way, making sure they don't make us look daft by doing a bad job and hopefully getting paid to do that. Or the bottom route is where they maybe just make switch machines at the moment, and we have to coordinate and do all the stuff, and that costs the partners more because they have to pay us to do all the stuff we don't really want to be doing, but we will do if we have to. And there's a long period of design and test, design including the manufacture side, so that the things can be made in numbers eventually. Field testing, when we do that, some things will go wrong that we haven't thought about, and we'll refine it a bit. And then we can go for assurance of the product, which means we've got a thing we can sell first probably to the UK rail industry, then hopefully around the world, because we've got patents around the world for this stuff. So eventually we deploy it. That's all good. So that's kind of where we're going a bit quick because getting toward the end. So some conclusions from all this journey over about 13 years or so. Yes. So there was a question at the beginning, could we rethink things and make things better? Definitely the answer to that is yes. So that's good. And I think we knew that quite early on, probably halfway through, at least we'd even proved it. So another thing, fault-tolerant systems like this still need some fault-tolerant control and some thinking about what happens when sensors fail and how the individual actuators might fail and things like that as well. The simulation models, I suppose it's one more bit of evidence that the models are good enough for designing the controllers and working out how big the motors should be and all of that kind of thing. So really useful exercise, but hadn't prepared us at all for the, with hindsight, obvious fact that each of those 6 motors would be slightly different and the friction in the gearboxes and so on would be slightly different, so that the load sharing wouldn't automatically come out. Yeah? And, you know, kind of obvious, but the bit that frustrates me, railways could save a fortune if they adopted this kind of technology, even maybe not repoint, but something similar. And a final thought about it, designing, building and testing things is hard work. It's a little bit frustrating, but it's a heck of a lot of fun. I mean, I've had a hoot, and there's nothing better than standing by the side of a railway and seeing a real track switch move with your ideas all happening. Even though you know it's going to work, seeing it work is wonderful. We wrote a lot of papers along the way as well, and I have to thank a lot of people, because it wasn't by any stretch of the imagination just me. So all sorts of researchers and colleagues that have worked with me over the past 12 or so years on that, and even before that, people who've given me ideas from some of the other industries. So thanks to them, and thank you to you for getting up early and sticking with me for the best part of 50 minutes. So thanks very much.
Hello. Yes, are there any questions? We have some minutes. You can ask some questions. I will move the microphone to you. So I will start with a question and maybe the audience. We see that you did a very nice new design in order to ensure fault tolerance by mechanical design, but there is a part of control system, and you designed the control system. But have you thought of also considering that the control performance can have an impact on the fault tolerance, and for example, the controller may mask the effects of a fault or may amplify the effects of the fault. So, during the design of the controller, have you thought, what if there is a fault? What will happen and how the control will handle it? Thank you.
Yeah, that's a very good question. Thank you. So the honest answer is, I don't think when we were designing the controller, we didn't think about that. But what we did do was some work with another PhD student who looked at constantly monitoring the electromechanical system and estimating using a little bit more complicated than just saying it, a system ID approach to estimate the parameters of the physical system. So we're estimating the friction in the mechanism and degradation of the motor and so on, and using that information to see if the system is degrading. Because as you say, the closed loop system will make that position performance, which is the thing we're really interested in, happen anyway, but it may be that the motor is providing twice as much torque as it was when it was new, because the friction's building up, or the mechanism's changed, or the motor's demagnetizing, or you've got shorted windings and all of that stuff. So we didn't design a controller to necessarily be robust to that or to mask that. We designed probably an add-on condition monitoring system for it. And what I didn't say at the end is, I imagine if we make this spin-out company work, that the thing that we'll be doing in 10 years as the money hopefully comes rolling in is still monitoring the systems for the railway network. So we'll be helping them to deploy these switch machines, and we'll be providing all of the data analysis and telling them when they need to go out and maintain things and how long they've got left. And we'll be still doing that university research type stuff, the clever bits.
Okay, thank you.
Thanks.
Are there any questions? Yes. So, Andrea.
Thank you for your nice presentation. So just, I have just a curiosity, but probably you have considered this problem. But in case you have iced rails, so do you have enough torque with the double motors to move and to lift the rails? Because of course it's a common problem in the North countries, and I know that you have considered. But if you can explain about a little bit more about this, and also what's going on in case you have a problem with one of the double motor. So because in that case, you have an higher rail and then the other one is down, for instance, no? How do you solve this? Thanks.
Yeah, thank you. So that's two questions. So I'll take the easy one first. So with the double motors, if one of those fails, we need to know that, and we need to switch off the remaining one in that bearer. It would be okay, it would keep operating, but it's not ideal that they're not both in the same position. So you're best to, if something's going wrong in one bearer, to remove that from the action. So we have a system that should do that in the higher control level. It was about ice, the next part, wasn't it? So a lot of people ask me this. Ironically, when we started the project, we were going to do all the testing at the Great Central Railway in the summer, which would have been lovely. In the end, we were installing it in November and December and testing it through the Christmas period and in January. And it was snowing and raining and miserable. So we weren't there to test it in horrible conditions, but it survived all those conditions. Did it have ice building up in it? No. But in terms of that, so those motors, certainly in the yellow actuator bearers that you see in the picture up the top right, we did test that thoroughly with 2 of those machines switched off and 1 operating. So there's no doubt that it can, in normal conditions, move the switch on its own, and using probably only 20% of the available current. So the motors were too big, yeah. I mean, we did the simulation, but we still added a factor because we couldn't afford to not have this move. Will it work in ice? So we haven't really proven that. I think it will, because I think it's easier to brake by lifting the ice that's on the slide chairs than it is with the current approach. If it does have some problems, most point switch machines have heating in, so we could always add that. But at least what the industry wants to hear is it will just work in icy conditions. I guess because I'm a researcher and an engineering academic, my honest answer is until we test it, we won't know. We think it's probably better than the current machines, but we don't have evidence yet.
Thank you. There was another question. Yes.
Thanks very much, Roger, for that very entertaining and interesting talk. There is a procedure spreading quite a lot these days about co-design.
Yes.
Yeah, and you know, normally as engineers, something is developed, you know, and you've explained all the stages of going backwards and forwards in development. But how much would it be valid in relation to the sort of discussion about the effect on fault-tolerant control of different controllers of different sense? You know, how valid would it be in the future, perhaps, in hindsight, looking back, to think of a co-design type of approach?
Yeah, so co-design. So I think we have, to a large extent, taken a co-design approach. I've maybe presented it in a little bit of an incremental fashion. So we've been doing a lot of interaction between the partners that are developing some of the big bits and us doing some of the small-scale electronic and electrical bits.
But it's the control issues and the fault-tolerance issues which actually need to be developed through the development of the system, you know, in my
Sure. So you want to design a system that's easy to control rather than make a system and say, here you go, can you make it go as fast as you can? And then the control engineer says, well, the limiting factor is this bad design thing. So we've used the simulation models along the way and designed the controller. So we've had the whole thing working before we've bought a component or started to make it. So I think we're doing that in the proper way. And I would call that a mechatronic approach to design. So the 3rd year course I teach on mechatronic design, we're talking about using those principles and concurrently designing everything, not just the control and the electromechanical system, the whole thing. And ultimately we need to do that, including the design for manufacture and reliability and all the rest. Yeah.
Thank you.
So thanks, Ron.
Thank you. If you have more questions, you can discuss over a cup of coffee. Thank you very much for attending the plenary. Let's give applause again to our speakers. Thank you very much.
Thank you.
Excuse me, just before leaving, good morning everyone. I have an announcement just to remind you that the social dinner, so you need to be for the social dinner at 7:30 at the former Theater Verdi. Please, if you need the directions, ask to the reception desk. Thank you.
attending this session about advance of fault-tolerant estimation and control. So the first speakers are Wang Zeyuan and Mohamed Chadli, and they will present their work about a virtual actuator and sensor approach for event-triggered fault-tolerant control of multi-agent systems.
Don't save. We'll save.
Welcome everyone, and thank you for joining me in this presentation. My name is Zeyuan Wang, second-year PhD student at University of Paris-Saclay. I'm fortunate to have Professor Chadli as my thesis supervisor and the co-author of this paper. So today I'm delighted to present our latest research on fault-tolerant control of multi-agent systems. I will start with the problem statement, then the proposed method in this paper. A simulation example will also be demonstrated as follows, and finally is the conclusion. So let's begin with looking at our specific problem in the context of multi-agent systems. Let's consider the leader-following problem with n follower agents and one leader. They are represented by the linear continuous time differential equation in equation 1. The leader here is actually a virtual signal without any control input, and this model is commonly used in the field of leader-following control of multi-agent systems. The objective here is to have the leader-following consensus, which is equivalent to have the difference of the state of the leader and the state of the follower convergent to 0. Let's also define some notations of the graph, such as the Laplacian matrix, leader degree matrix, and the matrix H equals the Laplacian plus the leader degree matrix. And these matrices are typically used in multi-agent graph representations, and we keep following these routines. Now, in normal working condition, there's no fault, and we then propose the nominal observer-based controller. The nominal observer is composed of this equation 3, where the xic hat is the observer state. We have the derivative of the observer state equals a times xic hat plus b times uic plus the observer gain AO times the difference of the observer output and the system's output. The nominal controller is uic, which is the controller gain big K times Zi, where Zi is the combination of the neighbor state and the state of agent I itself. So here Aij is not 0 if agent I and j are connected. The Di is not 0 if agent I is directly connected to the leader. The tilde xic is the event-generated state, because here we use the mechanism of event-triggered communication. So the state xi or the observer state, the hat xi, is not directly used in Zi, but the event-generated state, the tilde xic, the tilde xij. The tilde xic or xij defined by a model-based estimation as the value of tilde xic at the event instant tki equals the observer state, the hat xic. And between two consecutive events, tki and tk plus 1i, the tilde xic will follow the exponential law, or we say the model-based estimation, as the derivative of tilde xic equals a times itself. And notice that here the tki is the case event of agent I. And to measure the difference of the event-generated state and observer state, we define the epsilon as the event error as the difference of tilde xic and hat xic. We will also apply the technique of the event-triggered control, and here is the event rule in equation 5. The k+1 event of agent I is defined as the instant t after the case event once the function gi is 0 or positive. And gi is defined as minus eta plus omega times the combination of the quadratic product of event arrow and another quadratic product of control input zi. Here, the big U and big T are two matrices to be designed, and eta is the auxiliary variable with positive initial value, which follows the dynamic in equation 6. And basically, this DETM, dynamic event trigger mechanism, is an extension of the result in the famous paper of Gerard 2015. Note that we have in total 4 parameters to design: the observer gain LO, the controller gain big K, and the DETM gains big U and big T. They are a priori designed to have the asymptotic consensus. I will not present the detail of the design process, but basically they can be obtained by solving a set of matrix inequalities, and please see our paper for more details. So now let's assume that we have already well designed this controller and observer, and we have obtained these parameters. Now let's look at the system under faulty condition. Here we use the superscript small f to present the state affected by the fault. Note that the difference between the fault system and the nominal system is that the input matrix B becomes BIF and the output matrix C becomes CIF. And this is because we consider the multiplicative actuator and sensor fault. So here BIF is equal to B times the actuator effective matrix big theta I, which is a diagonal matrix with each element representing the effectiveness of each actuator. The effectiveness is between 0 and 1, so if it is 1, it means there's no fault, and if it is 0, it means we completely lost this actuator. Because we have m actuators, so the matrix big theta I is m by m. The output matrix CIF follows the similar modeling of BIF with the effective matrix big phi I. Each diagonal element small phi I is between 0 and 1. So this is how we model the fault. And when we study the multiplicative fault, the first is the loss of effectiveness is usual and common in the fault scenario. It means the actuator or the sensor can only perform a part of function or a part of efficacy compared to the normal actuator or sensor, and they are more difficult to handle compared to the additive faults. Besides, when we have 0 effectiveness, there is a problem of reallocation. And don't forget that we have also applied the event-triggered communication mechanism, so this is a big challenge in consensus control. And we're now at this page to summarize our problematic and assumptions. So we arise 2 problems to be solved in this paper. The first is, how can we guarantee the leader-following consensus in the presence of multiplicative faults? And the second is, how does the event-triggered protocol be synthesized in the presence of multiplicative faults? And to address these problems, we are going to adopt 3 assumptions. The first is the matrix pair AB is stabilizable and AC is observable, and the faulty process ABIF and ACIF are still stabilizable and observable. The second assumption is that the leader is the root of the communication topology, and the topology is undirected and fixed. The final assumption is that the fault values small theta and small phi are available. This means that, for example, we already have a fault estimation or a fault diagnosis module to offer a good estimation of these fault values. And I'll present to you the method proposed in this paper of fault-tolerant cooperative control by using the virtual actuator and the virtual sensor approach. The VA and VS can actually compensate the fault effect without retuning the designed controller. And this method is considered as a generalized approach of the pseudo-inverse technique, but can handle more general fault, including complete loss of effectiveness. Let's look at more details of the architecture of VA and VS. In the left figure is a nominal control without FDCC. The plant outputs YIC to the controller and gets the input UIC from the controller. The controller takes the YIC as the output and together with the event trigger mechanism DETM and generates the input UIC for the plant. And on the right-hand side is the fault-tolerant cooperative control. Notice that now we insert an additional green block between the faulty plant and the nominal controller. This green block is called the reconfiguration block, which includes the virtual actuator and the virtual sensor. Notice that the original channels of UIC and YIC are deprecated. Instead, they are moved to these channels between the nominal controller and the reconfiguration block. In fact, the system output is no longer YIC but YIF, and this signal is transferred to the virtual sensor, which generates YIC to the nominal controller. Besides, the virtual actuator takes the nominal value UIC and transfers it to UIF to the faulty plant. So in this scenario, the nominal controller remains unchanged, and it was like it doesn't care what happened outside the controller because the input-output relation is not changed. On the contrary, the faulty plant is reconfigured by the virtual actuator and the virtual sensor, so it's also called reconfigured plant. Now let me introduce the virtual actuator. The idea is to reconstruct the input UIF from the nominal input UIC. And recall that the virtual actuator is actually a more general case of pseudo-inverse method. So if there's no complete loss of effectiveness, we want to simply make this relation BIF times UIF equals B times UIC. That is, the UIF equals the pseudo-inverse of BIF times B times UIC. And now consider the case of complete loss of effectiveness. We add a supplementary signal MIVA times Xi delta for compensation, and the Xi delta is the state of the virtual actuator. And this is a more general case of equation 8, and the big matrix MIVA is the gain to be designed. And if there's no complete loss of effectiveness, we can simply make MIVA equals 0, and then equation 9 becomes the pseudo-inverse method in equation 8. The virtual sensor is actually a dual form of virtual actuator. It converts the faulty output YF to the normal output YIC. So similarly, if there's no complete loss of effectiveness, we can simply apply the pseudo-inverse method as in equation 10, as the YIC equals C times the pseudo-inverse of CIF times YIC. Otherwise, we introduce a compensate signal YIVS as the state of the virtual sensor, which follows the dynamic in equation 11. And notice that here, the big LIVS is the gain of the virtual sensor to be designed. The next step is to construct the synthesized formulation of the whole system. And before doing so, let's define the error variable as the consensus error delta IF, the observer error EI, the sensor error SI, and the event error epsilon I. We also define the vectorized variable as the delta F, ES epsilon, and X delta. Let's also define these notations. The A bar, B bar, C bar are actually the canonical product of the identity matrix and the matrix itself. So we follow these rules and we define also the K bar, AO bar, T bar, and U bar. The following matrices are also defined as the block diagonal matrix of small matrices of each agents as the M bar VA and L bar VS. So here the red matrices means the gains to be designed later, and the cyan matrices means the pre-designed parameters under no fault condition. And finally, we obtain the closed loop aerodynamic as in this equation. We now add the stage to apply the Lyapunov theorem by proposing the candidate function as in equation 19. We can verify that the V is positive if the Q and eta I are positive. And the objective is to find the sufficient conditions such that the derivative of V is always negative. I now present to you the final result in this main theorem. After studying the Lyapunov function, we obtain the result as follows. The system in the presence of actuator and sensor multiplicative force can still maintain the leader-following consensus if the following matrix inequalities hold. Here, the matrix MIVA is the gain of the virtual actuator, and LIVS is the gain of the virtual sensor. The matrix big T and big U are gains of dynamic event trigger mechanism. The matrix Sij are block matrices defined in our paper because they are actually quite long. We have proved that if these matrix inequalities are satisfied, the gain of VA and VS exists and the leader-following consensus can still hold. And actually, the above matrix inequalities are bilinear, so we do need global optimization solver. Also notice that the T bar and U bar as the gain of the event trigger mechanism are involved, which means the event trigger control may need to be updated according to the fault. Again, the nominal controller and the observer remain unchanged, which is the main advantage of this method. I also recommend you to have a read of this very similar paper which just came out after the submission of SAFEPROCESS. So at that time we were not aware of this study, but still there are many insights in this paper, so I recommend it for more information. And as a summary, I present here the FTCC procedure as follows. So once there are faults detected, the values are estimated and given as big theta I and phi I. Then we apply the main theorem to calculate the gain of virtual actuator and virtual sensor, as well as the gain of the DETM. Next, the agent I will insert the reconfiguration block between the plant and the nominal controller to activate the FTCC strategy. And finally, I present here a simulation example. The system matrices A, B, C are defined as follows, and the nominal controller and the observer gains are obtained as matrices K and AO. The communication topology is presented in this figure. The fault setting is described in this table. We consider simultaneous partial and complete loss of effectiveness on different agents. For example, between 5 and 10 seconds, the effectiveness of the second actuator of agent 2 becomes 0. And after 35 seconds, the effectiveness of the second actuator of agent 1 and agent 5 becomes 0. And after simulation, this figure presents the evolution of consensus error of different agents. And we can see that the consensus is well achieved. The dashed line actually means the occurrence of faults in corresponding agents. For example, we can see that at t equals 10 seconds, there is sensor fault in agent 1 and actuator fault at 35 seconds. And notice that the fault can propagate to the healthy agent. For instance, the perturbation of agent 2, 3, and 4 after 35 seconds is actually due to the actuator fault of agent 1 and agent 5. And then in this figure, we can see the inter-event time of each agent. It is quite evident that the inter-event time, IET, decreases each time a fault occurs, such as at t equals 5, 10, 20, and 35 seconds. And this is because the fault will bring more unprecise information when it is not fully tolerated. Therefore, the agent needs more communication to update and share the state. And finally, for conclusion, in this paper, we proposed a unified framework of fault-tolerant cooperative control for multi-agent systems under multiplicative actuator and sensor fault. We have developed a virtual actuator and virtual sensor-based approach which can handle the partial or complete loss of effectiveness. The dynamic event trigger communication protocol is also developed to reduce the usage of network resources. However, we also admit that there are some future works. For example, we have assumed that the fault value are well estimated, but if the estimation is not exact, how the estimation error can affect the control performance. And since we can only adjust the piecewise constant fault, so if there is a fast varying fault, can we adopt this strategy to handle this problem? And another practical concern includes disturbance and uncertainties, which should be considered in the future work. That concludes my presentation for today. Thank you for your attention. And if you have any questions, please do not hesitate to contact us, and we are always open for discussion. Welcome everyone, and thank you for joining me in this presentation. My name is
Okay, so for questions, you can contact the authors. Now I introduce the next speakers. So it is Ni Yuan, Yang Hao, Zhu Yuhang, Yin Bing, and Lu Ningjin, who will, from Nanyang University, who will present their work about a Stackelberg differential game-based optimal fault-tolerant control for overactuated systems.
Hello everyone, my name is Ni Yuan from Nanjing University of Aeronautics and Astronautics. I'm very honored to attend this conference. Today the topic of my presentation is a Stackelberg differential game-based optimal FTC method for overactuated systems. It includes 4 parts: problem formulation, main research, simulation, and prospect. In the problem formulation, first I will make a brief introduction to the overactuated system. An overactuated system refers to a motion control system with more actuators than what is actually needed to satisfy the control goal. One of the typical examples is overactuated spacecraft. Its actuators may include reaction flywheel, jet actuators, and so on. Such a system has many advantages. The most outstanding one is that the redundancy of actuators provides more possibility and flexibility for fault tolerance when encountering actuator faults. Here we give a linear overactuated system model, where X with a dimension of n is a system state and U with a dimension of m is a control input and m is larger than n. Considering the multiplicative and additive actuator fault, U can be further written into the following form, where F is the effective factor matrix and UA is a constant additive fault. Based on this assumption, we can and by introducing the virtual control input to replace the total control effort, BU, we can transform system dynamics into an equivalent system. And to deal with the redundancy of actuators, traditional methods of control allocation usually include 2 parts. First, the high-level motion controller, which is aimed to design the virtual control input V to stabilize the system state X. Second, the low-level fault-tolerant allocation strategy, which is aimed to design the control input of the actuators to make the total control efforts BU track the virtual control input V. However, such a method has 2 disadvantages. First, it ignores the allocation error between the virtual control input and the total control efforts BU. Second, it can only reflect the influence of high level on the low level, but it cannot reflect the interaction between 2 levels. And thus, we want to design a Stackelberg differential game framework to reflect the interaction between two levels and realize the overall optimization of them. In the main research, we will first analyze the relation between two levels. Motion control, the high level, is the basis of control allocation, the low level. And control allocation will affect motion control by state information. This relation is consistent with the Stankenberg game. Thus, we let motion control be the leader and control allocation be the follower and establish this Stankenberg differential game framework. For the leader, we introduce E, the allocation arrow, to represent the arrow between the virtual control input V and the total control efforts BU. And we design a revised system. And for the follower, we introduce A to be the decision variable to characterize the deflection rate of actuator output torque. Under this framework, the decision sequence is listed here. First, the value of the initial motion controller V is transformed from the leader to the follower, and then the optimal low-level fault-tolerant allocation strategy A star is solved by minimizing the cost function J1. And the last, the optimal high-level motion controller V star is solved by minimizing the cost function J2. First, we will focus on the low level. We have 3 optimization objectives. That is minimal tracking error, minimal control input, and the minimal deflection rate, which are consistent with the 3 terms in the cost function J1. And furthermore, to deal with the actuator faults, we designed the matrix Q into this form. As we can see from the formula, the smaller the effective factor Fi is, the bigger the weight Qi is, which means the lower the preference for selecting the actuator I is. And it can be proved that the optimal low-level fault-tolerant allocation strategy A star can guarantee that the allocation arrow E and the control input converge to 0. And then we focus on the high level. We have 2 optimization objectives, and that is minimal system state and minimal control energy, which are consistent with the 2 terms in the cost function J2. And as we can see, there is E, allocation arrow, in the cost function. And we can design the optimal high-level motion controller in the following form, where E can reflect the influence of control allocation on motion control. And when E is larger than 0, this form can help to decrease V to weaken the influence. And it can be proved that V star can guarantee that the system state X converges to 0, and it can form a Stankenberg equilibrium with A star. And since the 2 levels are coupled with each other, it's difficult to find analytical solutions of J1 star and J2 star. Therefore, we use adaptive dynamic programming to help us to approximate the solutions of J1 star and J2 star. And it can be proved that the approximate allocation strategy and the approximate motion controller can guarantee that the tracking arrow E and the system X are all uniformly ultimately bounded. In a simulation, we can consider the following system and set the initial state. The system first runs in the healthy case for 5 seconds, and the following fault occurs. And 5 seconds after the fault occurs, we design the allocation strategy. As we can see from the figure A, when the fault occurs, the system fails to keep the equilibrium. And after we redesign the allocation strategy, the system state can converge to 0. And when we see the picture figure B, we can see that we prefer to use the healthy actuators rather than the faulty ones. In the future, to further approach the actual situation, some factors such as disturbance, input saturation, and system nonlinearity need to be further considered. And we have already focused on the input saturation and made a research on the nonlinear overactuated spacecraft system. And the results have been published in the TAES. Thanks for your attention.
Yes. So does anybody have one question in the audience for this nice presentation? No question? So, well, I have one. Could you please go back to slide 12, please? You mentioned that you had to optimize both two objectives, minimum system state and minimal energy. And could you tell us a bit more how to balance between the two for systems? Well, you have some criterion to, but you set some balance between the two, or there may be some trade-offs also with Pareto, France, and so on.
There are two optimization problems actually in our research. That is, one is for the high level, the motion control, and one is for the low level, the control allocation. And in each of them, there are multi-objectives, and we can design the matrix to set the different weights to solve the trade-off problem.
Okay. And you mentioned as future prospects the dealing with input saturations, nonlinearities. Do you have some directions to push further in terms of methods? What kind of methods could be possibly envisaged to considered to add the management of input saturations?
The Stankenberg differential gain framework helps to establish a feedback mechanism in our research. It's like a feedback, and I think there are many feedbacks in the control field. So I think this method can be used in many other fields.
Okay. So thank you very much. And now I will introduce the next speaker, so which will present a fault-tolerant safe control for water networks with an interconnected switch system approach. This talk is presented by Meng Ginkai, Vrashimi Stelios, and Marios, and it is work from Marios Policarpou. So I give you you can start.
Okay. Good morning, everyone. My name is Qingkai Meng. I'm from the University of Cyprus. Today, what I'd like to present is fault-tolerant safe control for water networks, which is based on interconnected switched system approach. This work was funded by the ERC project and under the guidance of Professor Marios Policarpou. I will introduce my work from the following five parts. The first one is background. The motivation why we study the water network system, especially the drinking water, the drinking water transport system, is that such kind of system are essential infrastructures in our daily life with application in industry, agriculture, and other mining fields. such kinds of system has the following three characteristics. The first one is that they are complex because they consist of lots of components like pipes, reservoirs, and pumps. Also, they are wide geographical spread and as an integration of multidisciplinary technologies. The second characteristic is that they are safety critical system because they play an important role in public health, essential service, environmental impact, and economic stability, and so on. Also, the last characteristic is that they are prone to false disturbance and uncertainties. For example, the natural disaster like earthquake may cause the leakage of the pipes of such kind of system. So, to guarantee the reliability and safety of such kind of system, we should to design the fault-tolerant safe control scheme for such kind of system. We study this topic by using our test bed in our lab. It's consisting of one reservoir and 4 tanks. And these tanks are connected with the pipes. The water inflow the tanks by using the pumps. We can see picture B. Here, 4 tanks are connected with each other, so the overall system can be deemed as an interconnected system. Also, with the different set points of the wells and also the disturbance and force, each subsystem may exhibit multimodal dynamics. So each subsystem is a switch system. The overall system now can be modeled as an interconnected switch system. This is the model. Here, HI means the water level in one tank, and QI means the inflow rate. Here, we can see that with the different set points of wells, QI will exhibit 2 kinds of dynamics. So it's an interconnected switch system. We consider the disturbance caused by users' water consumption. As we know that such a disturbance may be periodic behavior because in our daily life, for different times of a day or for weekdays and weekends, the behavior of the user may be different. And also, we consider the process faults and actuator faults. The process fault is implemented by using the leakage of the tank. And the actuator faults, we consider the loss of efficiency about wells. Here we add the real well set point, and the UI is the effective set point. Then we can compact we can compare the system into such a nonlinear interconnected switch system. And here we integrated the process fault and disturbance as an integrated uncertainty. And what does safety mean? It means the state of the system will not go into the unsafe region. Here, we consider the safety limitation for both water level and inflow rates. It should be mentioned for different mode. It has different dynamics, so we can define the safety side for different mode. To design the controller, we need such kinds of 2 assumptions. The first one is that we assume we know the upper boundaries about the disturbance and force. That that means we should know the worst cases of the disturbance and faults in advance. And the second one is that the nominal system should be input to state stable. So-called nominal system is that a system without disturbance and faults and uncertainties. Here is the study aim. We want to design a distributed switching law and controller for each subsystem under the possible process and actuator faults. When the above two assumptions hold, it will make the overall system to be stable and safe. This is the diagram of our overall control strategy. The controller is designed following the following two steps. The first one is Barry function selection. Here, we introduce the distance between the reference state to the boundary of the unsafe site. This is unsafe boundary, and this one is the reference state. By using such form of Barry function, and under the assumption that the nominal system is stable, then we can show the state of the system will always be within the safe site. And the second step is to design the switching law. Here, we extended the classic state-dependent switching law design method with by combining with the Barry function technique. As a result, we obtain such a main result. It says that when we select such kinds of switching law, under the above assumption, the overall system will be both safe and stable. The main idea of the proof is listed below. The first step is to construct an energy function, which is related to both multi-Lyapunov function and Barry functions. And then we compute its derivative along the system dynamic with the design, the switching law and the control law. And then we check, here is not the derivative. It's to check the boundedness of the energy function, and then check the positive of the Barry function. The third step can prove the state will within a boundary of the space state, and last one will in place the safety of the system. For the simulation, we consider the water system operates over a week. Here we consider the water usage disturbance influenced by users' cyclical habits. We can see the blue curve. And also, they are influenced by the changing of the water level in the tanks. For the faults, we consider the sudden occurrence of water tank leakage in tank 1 here. And also the actuator loss of efficiency fault. I will show it later. And by using our controller, we can see the water level and the inflow rates are within the safe limitation. And this is the switching law response curve, and this is control input. The red one is the ideal set point, while the blue one is the actual one, which is caused by the actuator faults. Okay, now I'd like to conclude our work. We designed a fault-tolerant safe controller for water network system, which is based on the stability theory of interconnected and switched system. The key step is to selecting the switching law by using the local information. In our future work, the first thing is to design the active fault-tolerant control scheme, because here we need the worst disturbance and false assumption. And then we want to extend our result into larger scale and more complex water networks. Since here we only consider a system with 4 tanks. And also, if we improve the form of the barrier function, we can also obtain some other interesting result related to safety control. Okay, that's all. Thanks for listening.
Let's thank the speaker. Yes, thank you. Okay. So, are there any questions about the presentation? Yes?
Not a question, but on a remark. I studied the demand of water during the 1 year period because they are very seasonal, not on a week, but also month and amount of the season. And what I have observed was a very interesting thing because in the last night of the year, so-called Sylvester night, the demand of water is at least 4 times greater than enormous. Have you made any simulations with water demand changes that changes in a period greater than 7 or 6 days?
Okay, thank you, sir, for your remark. To be honest, I only do some simulation over some short time, and also you can see the simulation that here there is also some changing caused by the user usage, and also. And also, it's influenced by this term, which can be obtained by some real case. And I think that there are also some paper related to how to obtain such kinds of term. And maybe in the future, I will also do some work for a long-term change about this term. Okay, sir. Thank you.
Okay. Any other question? We have still time for 1 or 2 questions. Yes?
Thanks for your talk. I have a question about so you have used the Lyapunov function for stability and the barrier function for safety. So do you design them separately or as a single function?
Indeed, both Lyapunov function and the barrier function are used here to select the switching law. You can see. You can see here. I used the Lyapunov function just like the classic state-dependent switching law design, and I also used the barrier function h tau I here to select the switching boundary of the switching law. And assumption here is that the nominal system is stable. So here I only consider on the switching law design.
Okay, thank you.
Yeah, thank you.
may I have one more quick question?
Yes.
So here in the middle of these slides, you use the distance between
Okay.
XIRT to the space, and here you use consider the space of the whole space, which is unbounded, the whole space. I mean, remove XIRI. So why do you consider the whole space? I thought in the tank example you have, or the whole system is working with a bounded space, right? So my question is, why do you consider the whole space, whole state space R2 instead of the constrained space?
Here, indeed, here, for this safety problem, we only need to define the unsafe region, right? And here we only need to find some safe site which will not intersect with unsafe region. And then we can define the barrier function related our safe site. And if we can guarantee our state will always belong to the safe site, then the state will not go into the unsafe region. Okay, thank you.
Okay, yes, we have. Perhaps you mentioned the loss of actuator efficiency in your talk.
Yeah.
Could you tell us how do you model it?
Okay, sir. Here, I mentioned that the loss of efficiency is from the pump and the wells. Here we set the center port of wells with the ideal one to simulate the loss of efficiency actuator faults.
Okay. And you mentioned that water networks are highly critical systems in terms of safety. You propose a fault-tolerant scheme, but fault, you may have some, you may represent physical faults and try to achieve tolerance to them. But those networks may also be subjected to attacks, for instance, where the difference compared to physical faults may be the intentionality of the attack. This may have consequences on the scheme you propose or not, or well, what is your opinion about this?
Yeah, it's not on my proposal because we have also do some so-called security estimation after the cyber attack and also the resilience control for this topic. Yeah.
Okay. So let's thank the speaker. I propose to, unless there are any other very short questions, I propose to thank the speaker.
Thank you.
Thank you. So we can move to next talk. This talk is a joint work between 4 Chinese institutions. The first author, Shujin Wang, is from Nanyang University. The others authors are Minda Wang, Bin Yang, Ninjin Liu, Yaye Ma, Rongguan Li, Wei Du, and Ji Chao. And this work is about inverse page rank-based fault propagation analysis of production lines under multiple uncertain performance indicators.
everyone. Thank you for coming here. I'm Shoujin Huang. My advisor is Ning Lu. I'm going to present our work on fault propagation analysis for production lines. So, what is fault propagation? Fault propagation commonly exists in several complex systems, such as the computer memory controlled machine tools, production lines, and rolling processes. In the complex systems, if one part in the system encountered a fault, then the fault can be easily propagated to other parts of the system. And this phenomenon will reduce the safety and performance of the whole system. So it is urged to take some measures to measure this phenomenon. For example, identify the root cause node of the failure and determine the fault propagation path. For many manufacturing systems, we concentrate on production lines. Since production lines is critical in manufacturing systems, it is commonly consists of process or equipment. It is commonly used in manufacturing systems, and some work logs are generally retained for the equipment, recording several performance indicators. We can use these performance indicators to further analyze the fault propagation. Especially, it provides a potential for quantitative analyze this task. In production lines, there are several performance indicators recorded, such as the number of processed workpiece, the processing time, and the number of waste products. For each indicator, we can define the variance of the indicator, and then we can get the probability of propagation. For several indicators, we can get 3 probabilities. So there is a question. There is a problem. The several probabilities may be inaccurate, incorrect, or even conflict. To solve this problem, we propose a framework for qualitative and quantitative analyze the fault propagation to analyze fault propagation modes in production lines. The framework consists of 4 processes. The first is modeling, then fusion, and the next assessment, and finally diagnosis. Firstly, we use Bayes network to construct the model of the production lines. The Bayes network is very useful for this task because it can transform posterior knowledge into prior knowledge. Also, it is consists of topology and parameter. There are 2 parts. The left part is the topology, and the right part is the parameter. So it is very useful for further analysis. Then we can use DS evidence theorem to fuse the information, as we can use the performance indicators to define the propagation probability for each indicator. Then we can apply the DS evidence theory to fuse the several probabilities, and then we can obtain the synthesized propagation probability. The synthesized propagation probability is a posterior probability. before we have just got the probability. Then we can use the probability to accurately, quantitatively assess the risks for the propagation. In the field of computer science, there is a famous algorithm named PageRank algorithm. In a graph, if a node is important, if many other nodes jumps to it. However, in our fault propagation task, a node is important if the node can propagate to other many paths. So the PageRank algorithm and our task are inverse. So we propose a novel. Algorithm named inverse PageRank algorithm. It can use the before posterior probability to give an accurate assessment of fault propagation risks. Finally, using the obtained fault propagation risks, we can identify the fault propagation path. Firstly, we can use some site theory to diagnose the root cause node of the production lines. Then we can identify the fault propagation path. As for verification, the impeller production line is very important. Is a typical production line in many scenarios, and it is highly automated, tight coupling, and there is many typical casing failures in this production line. We can see we have analyzed the layout and equipment in the impeller production line. Also, we consider two performance indicators in this process in this production line. For quantitative analysis, we use 6 months history data for analysis. By using the proposed framework, we can obtain the model of the impeller production line. Also, we can obtain the fault propagation risk of the fault propagation risk. To give more information of this problem, we also transform the left graph into the right graph. By transforming the edges into nodes, we can derive the auxiliary Bayes network. Use our inverse PageRank algorithm. We can assess the risks of equipment and the age. We can see that our result, the root cause node is node V1, and the propagation path is V1 to V2, to V3, and return V2. Finally, to verify the effectiveness of our proposed method, we consider two aspects. As for the first aspect, we consider whether our result is aligned with the mechanism our propagation path is control qubits to robotic arms, to CNC machine tools 1, to robotic arms. This aligns with the mechanism. Also, as for the second aspect, we consider the typical casing failures recorded in the impeller production line. We can see the red figure. We can see that our proposed method is aligned with the typical casing failures of engineering. So our method can achieve satisfactory results in our task. As for future work, we can consider data and knowledge draw-driven method. Also, we can consider a complete analysis framework. We can combine fault diagnosis and fault propagation analysis. Fault diagnosis can be regarded as a prior process of fault propagation. Therefore, it is very meaningful to combine the two processes to analyze our system or work. Thank you.
Thank you. Some questions for the speaker and this nice presentation? No question? So perhaps one. So when you propose a method for fault propagation, you mentioned at the end some future prospects related to diagnosis, but do you consider some differences between diagnosis that is finding the source, the original fault, or you can also consider modeling the propagation of several faults rather than just having some probability that one fault, whatever it is, occurred. So my question is, you presented how to propagate. Can you make the analysis for different kinds of faults, that rather than evaluating general risk in the propagation?
No, I haven't considered different types of faults. And this can be a direction of the future work.
Okay.
Thank you.
And okay, any questions for? So well, let's thank the speaker again. So the next speaker is Silvio Simani and Ping Lam, and it is a joint work with Ping Lam Yat, who will present their work about data-driven adaptive fault-tolerant control for floating offshore wind turbines.
I don't know if it's better to wait a couple of minutes, yes, because
yeah.
we maintain the schedule.
Yeah,
it's better.
Okay.
People need to change rooms. So. If you agree, it's just a
of course. Yeah.
So I can start just introducing the framework and explaining also this cooperation. Well, this before entering into the problem, well, we have this, we call this a sandwich program, which is a student exchange program between Tokyo in Japan and the University of Ferrara. So this program is not really supporting students visiting from Ferrara to Japan, to the campus, and it's just our students are waived from the scholarships, and they have an announcement especially in the accommodation. So is something that is trying to enhancing this exchange, and our students can select English. Shibara Institute of Technology is offering, I think, about 150 courses in English. So is why this project is of this exchange program is quite interesting. It was started with a former colleague of mine who was working in our department, while really in the electronic for the ICT area, and then he moved for 3 years in UK as a lecturer. And so I replaced him with this charge as now I'm also the international coordinator for student exchange programs like the Erasmus program. Of course, in the area of information science, because every area, so mechanical and civil engineer and computer science have their own one delegate for each area, and then we have a departmental coordinator for all the areas, which is a delegate of the head of the department. So it's why we started this work. Well, I also need to apologize for Yat Piglam because he was unable to come here. He's finishing now his PhD program. We don't have only this student exchange for bachelor and master degrees courses, but also we have also exchanges as PhD students. So it's why supported by one local coordinator is is quite new also for me, this research area, because I'm mainly focused on onshore and offshore wind turbines. So through this program we started, I had some small contributions to Yat Piglam works, especially in the, I gave him some suggestions how to implement. I will start in a couple of minutes explaining it, in the adaptive approach for the compensation of the fault effect. So he tried to implement a fault-tolerant control system applied to this benchmark. And then I recommended him to use a Monte Carlo analysis tool, as Professor Ron Patton in his plenary speech yesterday suggested, and in some previous works also with Professor Patton, we used the Monte Carlo analysis not only for the analysis of the results, that especially as in this case you have only a benchmark, a simulator, can be also used as a tool for a co-design. As we had a project in 2005, it was involved the European Space Agency, and the Monte Carlo tools was included in this project, not only for the final verification and validation of the results, but also for the design of the fault. It wasn't fault tolerant, but we need only to develop a fault detection and isolation module for the thrusters of the Mars Express system. And the last contribution was that I helped with my student, was to use a hardware-in-the-loop simulation tool in order to validate, because we were unable to, this time, to try and apply the solutions that Yaping Lam developed. So it was a first way to try to find like a real test case. It's not real, but in some sense is able to provide you with the first step of validation on an almost real system. Well, the part of which is simulated is represented by the floating offshore wind turbines, because it's implemented in a micro computer, in a microcontroller, and so you have, as I will show later, you have the hardware interfaces, and then this, which is called hardware in the loop, because you are implementing the solutions that are developed in a software way. They are implemented it was an hardware that we used for the benchmark competition that was mentioned and started in 2009 in a previous war, SAFEPROCESS.
Thank you very much, Silvio, for this nice exercise that I imposed to you. And well.
Okay, now I can start with the focus on this project. This project is a joint project, so again, as maybe somebody is joining now, is a joint work between a visiting student with this university in Japan, and myself. I gave just, let's say, 2 or 3 recommendations to Yaping Lam, who he couldn't be here, so he's apologized for and we prefer to, I suggested him to just not to send a recorded video, so I'm trying to to explain as far as I can. A lot of work, especially all the technical development, or everything, also the software development was performed by Yaping Lam. He did a lot of work. Of course, everything is not included in this paper that is published because it's too much, and it represents just a small piece of researches that are developed by Yaping Lam, and they will be included in his PhD project. So it's something, it's just one topic, and another topic which will be contained in his thesis. It will be presented tomorrow again by myself in another session. So I will start with some motivation, very basic background. I will not enter into the details of, especially in the model description. I will focus just, I will give you a general idea of the tool, and we will try, I will try also to explain as far as I can the results that Yaping Lam obtained. And I will conclude the presentation, of course, with some other open problems and conclusions. So, the motivations are clear because floating offshore wind turbines are very popular due to adaptability to deep water applications. Of course, it's really challenging the control of floating offshore wind turbines, especially when you include not only control, but you want to implement a fault-tolerant system integrated with the controller. In fact, one of the final comparisons that we propose, it will be with the baseline, let's say, controller already available for this benchmark, and the integration with a fault-tolerant controller, which is an active adaptive controller included in this. And then we compare it with some other previous solution that we proposed in our previous investigations, but they were applied just to onshore or offshore wind turbines, so nothing was already tested on floating wind turbines. Well, it's model-free, because especially model-free is this term is applied for, especially for the development of the solution of the fault-tolerant solution. So we don't need the model of the system, because through an adaptive, quite complex adaptation mechanism is a nonlinear real-time dynamical system, which I will show in a while. And of course, the baseline controller was developed by using the model of the system. So the baseline controller is model-based, but the solution that we are providing is model-free. So this is the sense of this work. So we are using both individual and collective bridge control for fault compensation. So we are comparing both the approaches. Well, this is interesting because as it was recommended or is a general driving direction, we are the fault detection and the isolation or the fault diagnosis in general is not needed. So it's why the problem is recasted into a real-time control solution for nonlinear system. And then we will see some simulation first, and then some tests, as I already remarked, on hardware in the loop and Monte Carlo simulations. So the final results are listed here. So the wheel bearing load balance is maintained. We are able, I just left some results, the most important results. You can see that the movement of the floating platform is reduced. Also is reduced the bearing loads, and another performance metrics is represented by the fact that the compensated power is close to the fault-free generated power. So this is another performance metrics that we are using. And finally, this solution represents a way for proposing a fault-tolerant system for, especially, so it's clear that we are monitoring the blade root moment sensors and the fault that are included in these sensors. So the state of the art is that is considering that these systems, of course, they are subjected to higher structural and fatigue loads. And this leads, as also Professor Patton suggested, recalled, we have a rapid wear or damage of the structural components. And of course, we need to have, to achieve a reduced, to limit the reduced service life with increased, of course, which leads to increased operation and maintenance costs. So the solution, as already mentioned, is a model-free adaptive fault tolerance individual pitch control system scheme for blade root moment sensor faults. So without any a priori modeling of the floating offshore wind turbines. So it's different from, I tried to also cut some slides because the original presentation was of more than 40 slides, and it was really impossible to present everything, so I need also to summarize some of them. And so also I will show the case of just one sensor fault, even if in the paper we presented or in the standard version we are preparing for a journal, we will show all the fault cases that are considered. And so, again, the solution is based on an active fault-tolerant control strategy, which is able to, without using any fault detection and diagnosis module, is able to dynamically recover multiple, not only the single, but multiple blade root moment sensor faults through an adaptive compensator. So the solution, just I tried to, as I already mentioned, so the individual pitch controller is based on a model-free adaptive control method, which is able to cope with modeling error and unmodeled dynamics. Again, we don't need any fault diagnosis and isolation module because the dynamic fault compensation is transformed into a nonlinear system in real-time control problem. Everything was tested with the FAST code. FAST means fatigue, aerodynamics, structure, and turbulence code, which allows first to show the effectiveness of our solutions, and the second contribution is that I suggested to try to test the solutions to hardware in the loop that was already proposed for offshore wind turbine benchmark competition. So this model is based on a benchmark which is supported by the NREL. It includes structural dynamic floating systems which are modeled in this benchmark. I will show later a picture of this benchmark, which is available also in the network. It contains an individual pitch control system. There are some faults affecting the system, especially the blade root moment sensors. Of course, these sensors lead to unreasonable, so they are not admissible, the pitch angles. It leads to unbalanced the wheel rotation and, of course, poor performance, for example, in the power generation, and also the wind turbine, if possible, the wind turbine damage. So this is the scheme, the general scheme of the model, and we are considering the pitch angle, which is the angle of this axis. And so which kind of faults are considered in the blade root moment sensors? So we are considering fixed bias, drift bias, or also the situation of, let's say, almost complete failure. We have also another fault case which was not included here, so it was representing the loss of the accuracy of the measurements. So is represented, is modeled with this relation, and especially so the real root moment is linked to the true root moment through this parameter, which is the fault factor. This fault factor is 1 when there is no fault, and is fluctuating between different values in case of faults. So the idea is that the compensator is trying to estimate this parameter in order to compensate it, as we will see in the scheme at the end. So the idea, just to try to summarize, is that normally it's difficult to find a model for the overall control system. So it's why we considered this solution, which is a model-free solution, and is particularly important because the sensors are used in the feedback, in the control loop, so it's very important to compensate them. And as again Ron mentioned, so Professor Patton suggested several topics that are covered here. We are using a transformation, a rotation transformation, which is commonly used, is introduced in different areas of, for example, brushless motors, also for modeling the asynchronous motors. In that area, they are called Park and Clark transformations. Here are called Coleman transformation because it depends on the pitch angle. So in fact, this is one of the relations which links the three components of the moment to the tilt and yaw angle of the system through the platform pitch angle. So this is one of the relations that are used. And after this transformation, everything is, after this Coleman transformation, everything is ruled by this equation. I tried to summarize this equation. Well, of course, as it's written here, doesn't mean anything because it involves a lot of nonlinear relations to an adaptive scheme, which is included, just summarizing the paper, because as you know, in the conference papers here, you are allowed up to six pages. So we cannot include everything, all the description of the system. And finally, you have how this is translated is converted into the components of the three blades of the system. So everything again is transformed to the inverse Coleman transformation, which links the pitch angles to the output of this dynamic nonlinear filter discrete time. So they just again summarize how this scheme works. So all the sensor faults are summarized by this fault factor, which varies with values lower than 1, also negative values. And there will be a fault equivalent compensation factor, which is estimated by this adaptive nonlinear approach. This approach involves also, is not reported here because it takes several slides just to report all the adaptation mechanism, and is using like a dynamic optimization, nonlinear dynamic optimization of the problem in order to find the optimal factor which compensates the is similar to the Lagrange multiplier solution, which is included in this system. So normally, when there is no fault in the blade root moment sensor, so the three blade movement varies periodically, and of course they are the same except for the difference of 2/3 of pi. Of course, when a blade root moment sensor failure occurs, this inaccurate moment values is fed back, so it's why it's quite important to compensate it, and it results in an imbalance of the loads on the three blades, and this imbalance, in this case, is transformed in this way, so this is the system to convert everything. So we are considering, just to arrive, because I think I almost just a couple of minutes for concluding. Sorry if I wasn't really able to summarize everything. So we have the case, just I reported this, table, that in case of fault, we have the nominal values of the moments, but in case, so without fault, we have this situation, and with a fault on a sensor 1, you can see here the big deviation of the moment. So it represents the effect, which is also nonlinear. It affects also the other 2 moments, but the main effect is on the moment. This is due to the structure. So depending on the value of this factor, it's also the fault propagates into the system. So I'm just trying to summarize and come to the results and the conclusion. So we are proposing this adaptive compensator. This is the whole scheme, so it's very similar to the other schemes that are available. We have the baseline controller, which is integrated with this adaptive fault compensator, and we have here the effect of this system. So in order to summarize, we performed also some comparison with passive approaches we developed in previous researches. And in order to summarize, you can see here that with the solution proposed in this paper, the oscillation, for example, of the floating platform is reduced and the generator power is closer to the rated one. I don't want to comment more results. And the second result is also a comparison with respect to the, for example, the power generation, which is closer to the rated value when, for example, here the adaptive solution is proposed. We have, just skip again, I want to show you here the case, well, in blue you have the solution without fault compensation, and in red you can see here that in case of fault, for the different case, the performances are closer to the reference case, so the case without faults. And in order to validate, I'm just closing, I propose to use both a Monte Carlo analysis and a hardware-in-the-loop method. So this is the final table. So you can see here there are some deviations, of course, when you are modifying the parameters of your model and consider the nominal solution, which is worse when you are considering the hardware-in-the-loop simulation, but of course, because you are introducing some real-time also aspect of your system. And okay, I'm concluding. So sorry if I had to skip some details, but so the main achievement of this work is a data-driven. Sorry for the typo, the individual pitch control technique, which is integrated with a fault adaptive compensator. This is able to reduce the problem associated with sensor faults that are propagate into the system and deteriorates, of course, the performances of the system. And we try to validate our solution with a Monte Carlo analysis tool first, and then with the hardware-in-the-loop solution. Okay, thanks for your attention.
The speaker. Due to the time, perhaps a very, very short question about the strategy used for the design of experiments. You talk about Monte Carlo simulation to represent meteorological uncertainty, environmental uncertainty. Did you use some specific strategy for the design of experiments?
No, normally, well, what we tried, well, it was simple, so maybe as you suggested, we need to include, as also Professor Patton remarked in his very wonderful plenary, we can introduce also some aspects. Normally, in this simulation, because we need some quick results, we just modify the parameters of the model. But as you recommended, yes, it's something that we will consider in further works. Thank you. Yes.
Okay, let's thank...
Just a short question.
Sorry, let's go.
The topic of your presentation is about data-driven...
Is in the solution?
Yes. My question is, in which context the data-driven approach is used? Is for to complete the models or to...
Is for in the design of the solution, the adaptive solution. It does not need, it's just based on the data.
Okay, thanks.
I hope this answer, we can talk about it later if you want. Thank you.
Okay.
Thanks again.
So the last presentation of this session is proposed by Shengzu Ren Yayi and Cao Shunhui, who will present their work about synergetic decomposition of input-output dependency for control system intelligent monitoring, a perspective from information theory. Yes, you can.
And I'm from Zhejiang University in China. I'm delighted to have this opportunity today to share our work with all of you. The focus of my presentation revolves around a novel approach we have developed for fault detection in control systems from an information theory perspective. I will introduce our paper through 4 parts. First, let me introduce background about our search. Timely detection of anomalies in industrial processes is crucial for ensuring production safety and maintaining product quality. With advancements in artificial intelligence and the Internet of Things technologies, data-driven fault detection methods have gained widespread attention. These methods involve collecting normal operating data from industrial processes to establish fault detection models. During online application, if the monitoring statistics of a new sample exceed a predefined range, it is considered a fault occurrence. Industrial processes rely on control systems to ensure stability and efficiency in their operations. Given the critical role of control systems in industrial processes, any fault can lead to production interruptions or a decline in product quality. Therefore, timely detection of fault systems faults is very important. In control systems, input variables and output variables play distinct roles. Input variables provide the excitation signals to the control system and influence output variables. Output variables, on the other hand, are the results generated by the control system after processing the input signals and internal logic, reflecting the state information of the process. To achieve fault detection in control systems, existing methods can be classified into 2 categories: static methods and dynamic methods. Static methods employ statistical learning or machine learning techniques, such as PCA or autoencoders, to establish fault detection models for input and output variables. However, these methods overlook the temporal relationship between the variables. To address this issue, dynamic modeling methods have been proposed. A typical example of dynamic modeling is the canonical variable analysis, which describes the state space of the process. As shown in the figure, the current output state is influenced both by the transition of the previous output state and by the input excitation. This reflects the temporal relationships between input and output variables. Now, let's take a look at the issue mentioned above from the perspective of information theory. The core question we want to explore is that how the information contained in the inputs and outputs of the previous moment transmitted to the output state of the next moment. Before exploring this issue, we need to understand the related theory of the information bottleneck. In the information bottleneck method, data is viewed as random variables containing different degrees of useful and redundant information. The model needs to squeeze information out of a bottleneck, removing redundant noise and retaining only its most critical features. Let's look at this figure. Input data X is used to extract feature C for predicting output Y. In this case, the information bottleneck requires that the mutual information between the extracted feature C and its output Y to be maximized, while minimizing the mutual information between the feature C and the input X. By the way, mutual information is a concept used to measure the correlation between two random variables. It describes the degree of dependence between two variables. That is, how much information can be provided about one variable by observing the value of another variable. These variables can also be high-dimensional. In simple terms, the information bottlenecks requires that the feature C retains the information most related to the output Y, while avoiding irrelevant information from the input X. We express the optimization objective of the information bottleneck as follows, where beta is used to address the weight of the two mutual information terms. It can be found that the expression of the information bottleneck is very concise. However, this optimization problem is very challenging to solve because the mutual information is very difficult to calculate. Let's look at this expression of mutual information. In many cases, the probability distribution of variables is unknown. To solve this problem, some scholars proposed using variational inference to estimate the lower bound of the information bottleneck. This method is called variational information bottleneck. We will not conduct a detailed derivation here, but if you are interested, you can see it in reference to. In neural network models, after a series of complex computations and approximations, the optimization objective of the information bottleneck can be transformed into a prediction loss and a regularization term. Let's look at the first term. The E denotes the expectation in probability theory. Combined with the neural network model, it can be understood as using input X to obey feature C and to predict output Y, requiring the prediction to be as accurate as possible. The first term ensures that the extracted feature C contains useful information. This prediction loss is usually expressed in the form of MSE loss. The second term is a regularization term, where the KL divergence is used to measure the difference between two distributions. And RZ here refers to a Gaussian distribution. Therefore, The second term indicates that the information bottleneck requires the extracted feature C to approximate a Gaussian distribution as closely as possible. That is, it ensures that the feature C contains a certain simplicity and structure, preventing the model from overfitting noise and outliers in the input data and thereby removing unrelated details from the input X. After having a basic understanding of the information bottleneck, let us now introduce the proposed method. This is a framework of the proposed method, where U denotes the input variables of the control system and X denotes the output variables. For the control system, we have the following two understandings. The information contained in the input and output variables at the previous moment determines the output at the next moment. That is, this information has a predictive effect. For the individual input or output, the information it contains can be decoupled into predictive and non-predictive ones. Based on these 2 points, we construct the optimization objective of the proposed SD-BID method as follows. Next, we will explain the meaning of each optimization objective in detail. In the first optimization objective, we decompose the output variables X into predictive and non-predictive features, requiring these features to contain the main information of the output variables, enabling complete the data construction. The variational inference expression for this objective is as follows. Due to time constraints, we will not dive into the details here. Similarly, the input variables U are also required to be able to reconstruct themselves, using the same variational inference approach. In the third optimization objective, we extract features Cx and Cu from the input and output at the previous moment, respectively. We require that these features contain important information that can predict the output at the next moment. Therefore, we hope the mutual information of the concatenate features and Xt to be maximized. In the fourth optimization objective, we require that the extracted feature Cx should remove irrelevant noise information from the input variables. So the mutual information between Cx and the input variable should be minimized. The same approach is applied to Cu. Now, by merging and simplifying the results of each of the above objectives, we can obey the following form of the loss function. Through gradient descent, we can optimize the neural network parameters to achieve the training of the SD-VRB model. After training the model, we design 3 monitoring statistics for comprehensive fault detection of the control system. The DF statistics is obtained by calculating the prediction error. This statistic can describe whether the output state of a control system follows the temporal relationship under the influence of input excitation. The DP and the DI statistics are obtained by calculating the construction errors of the output and input, respectively, describing the cross-correlation in the output and the input variables. Then we will demonstrate the effectiveness of our proposed method by tendency Eastman process. TEP is developed to provide simulation data of an industrial process with control systems, which contains 41 measured variables and 11 manipulated variables. There are 500 samples in the training set. For the proposed SD-VIB method, we take manipulated variables and measured variables as inputs and outputs respectively. Afterward, we selected 15 types of faults as a test set to validate the effectiveness of the proposed method. The neural network structures for each component of the proposed model are illustrated in this figure. Let's take fault 4 as an example. In this case, the reactor cooling water inlet temperature suddenly increases at the 161st sample. This variable can be controlled by reactor cooling water flow. Under the influence of the control system, the temperature quickly returned to the original set point. We compare the results of PCA, CVA, and DMD for fault detection. It can be found that all the statistics of PCA and CVA exceed the control limits after the 161st sample. In the case of DMD, the first two statistics describe the dynamic characteristics of the process, while the last two statistics describe the static characteristics. These methods fail to explain the input-output behaviors within the control system. Regarding the proposed SD-VIB method, we observed that only statistic DI consistently exceeds the control limit, where statistics DF and DP can quickly return back. This is because the input variable has continuously deviated from its regional distribution after the occurrence of the fault, leading to the changes in cross-correlation among the input variables. On the other hand, the output variables have been quickly controlled, maintaining its regional relationship. Through the proposed method, this fault can be understood as a normal response of the control system. The input information has undergone changes, which can serve as a warning for on-set operators. Compared to other methods, SD-VIB offers stronger explainability. We evaluate the performance of different methods using false alarm rate and missing alarm rate. It can be found that the proposed method shows the lowest false alarm rate. Finally, we can draw some conclusions about our proposed method. In this work, we reviewed the complex dependence relationship between the output of the control system and its input from an information theory perspective. The proposed method decouples the dependence into the cross-correlations between the input variables and the output variables, as well as the temporal relationship between them. Then, 3 statistics are designed to provide comprehensive monitoring results. The effectiveness of the proposed method is illustrated by TEP. Thanks for your listening.
So for questions, I suggest that you directly contact the authors. Before closing this session, I propose to thank the organizers of that invited session, who are Yang Bin, Marius Policarpou, and Meng Ginkai. Thank you.
Hello and welcome to this plenary speak by Olof Steinert. My name is Erik Frisk. I'm a chair and I have a co-chair sitting there. So the title is Predictive Maintenance and Collaboration to Boost Innovation and Harnessing Data for that. So speaker is Olof Steinert. He has a Master of Science from Engineering Physics at Chalmers University in Gothenburg, Sweden, and also a Bachelor in Economics. He works as a data scientist specializing in predictive maintenance at Scania. Scania is a heavy-duty truck manufacturer in Sweden. And at Scania, Steinert has actively contributed to advancing data science, especially within predictive maintenance and health monitoring. He has continued to write research papers and patent innovations. And I can speak for myself. We have had collaborations in research, and this has been very fruitful. And I think this is an advanced use of predictive maintenance in an interesting industrial application. So with that, I leave.
Thank you, Erik. Thank you for this opportunity to come here and speak about how we are leveraging data and modern technology to achieve state-of-the-art predictive maintenance. It's a fantastic venue, also a little bit scary, but I wasn't imagining myself on a theater scene when I was signing up as a data scientist at Scania, but you never know what the future has for you. Yeah, so this speech will be about the predictive maintenance, but I will also talk a little bit about how we are underlining the importance of collaboration and partnerships and daring to share to actually stay ahead of the competition in this field. But just to set the scene a little bit, for you to understand why predictive maintenance is so important for Scania, I want us to think or put ourselves in the shoes of our customers. So our customers, they are transporting things, transporting goods or people, the trucks and buses. And let's take a quite extreme example where we have a customer doing temperature-controlled cargo. It could be medicines, life-saving medicines. And in this case, our customers, they have a really, really important job. They need to ensure that the cargo the medicine arrive to the patients in time and in good condition, so they shouldn't have been destroyed on the way to the patients waiting for them. So very important job. What would then be a nightmare scenario? I mean, one nightmare that I could imagine is that the truck gets stuck in the middle of nowhere, not even close to repair facility. And yeah, that's something that I would do quite a lot to avoid. I want to avoid this harm to my reputation as a transporter. I want to avoid this inconvenience for the patient, or even not being able to save the lives. And this is where I see that predictive maintenance comes in, and this is why it's important for Scania, and this is what we will talk about today, how Scania is working with data and advanced technology to stop these disasters before they even happen. But before we jump into the main discussion, just explaining who we are at Scania. I know this is boring, and you don't need to remember this, but just for you to get the context right, we are a producer of trucks and buses, or that's not what our CEO says. I think he wouldn't be very happy with that explanation, because we are trying really, really hard now to go from a traditional OEM to a service provider. So now we are saying that we are driving the shift towards sustainable transport. And we see it as our purpose to break this connection that we have today between an increased need for transport in the society and the increase of congestion, the increase of accidents, and of course of CO2 emission. So just looking at what we do, yeah, here you see, it is actually quite a lot more than trucks and buses, even though they are still the main things. Our trucks, we do trucks mostly long haulage, but also trucks for construction, distribution, public transport, which could be refuse collectors, it could be fire trucks, those kind of vehicles. Then we have people transport solution, which is basically buses. There we also have a quite complete offering, buses for the inner city and buses also going from Sweden to Italy basically, like for tourism. Power solution is when we use our engines that we normally put in a truck for something else. It could be here as in a ship, it could be for a generator set. So not only goods and people, but also actually providing electricity where it's needed. And then, of course, services, both financing and workshop and driver services that we will talk more about. This quite, a very short version of Scania. We are existing almost everywhere, not so much in North America, but in more than 100 countries. 57,000 employees, and we have a service network spread out in locations where our customers are operating, no matter where they are operating. Then we see, that our industry is changing. There is a growing demand for sustainable transport in the world, and this demand is driven by global factors, and these global factors are also influencing the tools and the technology that we are using in our industry. And the main drivers for these sustainable solutions that I talk about is automation, connectivity, and electrification. And for those of you who don't think trucks will run on batteries, our estimate is that we will in approximately 5 years have half of our new sales volume being electrical vehicles. So this is how fast this shift is going and how fast this shift must go for the climate. Enough about the background. Now jump into the main topic, our uptime services. At Scania, I think most companies would want to say that we have a customer-centric approach. Which means that we recognize the fact that our customers needs to be profitable for us to be profitable. And the way we can make our customers more profitable at Scania is, either we decrease their costs or we increase their revenue. And as I see it, predictive maintenance and other uptime services, addressing both these things, if we manage to avoid unexpected interruptions of the operation, we managed to avoid additional costs that the customer would have. They would need to have another driver, they would have hours of replanning, potentially fines connected to the transport mission. So all those costs we could decrease by avoiding these unwanted situations. And at the same time, our customers are making money when they are on the road, transporting things. And if we free up time for that, we are also increasing the revenue potential. So that's why it's very important.
All transports are important, but some are more critical than others. And no matter if you are making just-in-time deliveries, transport perishable goods, or have made an extra important customer promise to secure a contract, Scania ProCare is the service that ensures you will always deliver on that promise. By using 24/7 monitoring and advanced algorithms, ProCare makes accurate predictions about individual vehicles' wear and maintenance needs, based on its specific data and usage, combined with the insights from hundreds of thousands of connected vehicles. The system automatically notifies your local workshop when a component is due to reach end of life, so they can order it in advance and replace it before it actually does. All done at your next scheduled maintenance visit. And to scale with any size fleet, this top-tier uptime service contract is available on a per-vehicle basis. With coverage for every uptime critical part of your vehicle, you can focus on your operation, and we'll make sure your vehicles stay on the road. Scania ProCare is the key to ultimate uptime for your most prioritized transports.
So I thought it was best explained with a film. So this is how we package our uptime offer. And I don't know if you understood it from the short film, that we see that our uptime, this is our premium uptime service, is built up by two main capabilities. And these are these 24/7 health monitoring, real-time remote health monitoring, which allows us to detect problem, hopefully at least, before they are noticeable for the customers. We can intervene and make this go away as quickly as possible. And then we combine that with this data-driven maintenance planning where we are managed to avoid unexpected interruptions by preventively replace some of these key driveline components. And yeah, we talk about 100% planned uptime, a little bit like a politician. It's not 100% uptime, it's about plannability. And this is what I wanted to illustrate with this graph here, that from our customer perspective, they want peace of mind. They want to focus on what they are best at transporting. And for that, they need a plannable operation. But plannable operation can mean a lot of things, and I think this is a message I really want to share, because our use case is not one thing. It's not only about, in this midterm equipment planning the maintenance so we avoid interruptions. It's also about knowing your transport capacity, trusting that you can do the transport mission that you sort of sign up for. And also in the short term, everything will not ever be planned. I mean, these random events will happen. A stone could hit the NOx sensor, or a shit hit the fan. I mean, then it's about minimizing the disruption for the customer. It's not about planning these things, but for the customer to be able to plan with the support from Scania. So from a customer perspective, it's about eliminating unplanned downtime. And I mean, that's a huge thing, avoiding these fines, having this peace of mind, being able to focus on what you're good at. So I mean, that's a convincing argument for doing predictive maintenance and uptime services, only that. But the nice thing here is that, I mean, when we sell this as a contracted service, there is also an upside for Scania on the cost side. We decrease our service production cost when this is efficiently implemented. And the way we decrease this cost is because we go from something that is unknown and unplanned in our workshops to something that is known and planned, which means that we can remove any troubleshooting work. We don't need any towing. We don't need extra overtime hours. So all those cost decrease are benefiting Scania at the same time as this minimized disruption are benefiting the customer. And that is what I call the sustainable business model. So reliability and availability of vehicles, I mean, that's very important. I think that is what I want to have said already. And what's predicted for the future? Will it be less important? I'm arguing no, it will be more important. With electrified and autonomous vehicles, first of all, the tolerances in the transport system will be much smaller, so the acceptance for any downtime even smaller. But then also with autonomous trucks, we lose a sensor, the driver, who can touch and feel, see and hear things. That we need to replace with something else. And here our belief is that we will need to put confidence in the data and the sensor technology in the vehicles instead. Okay, so hopefully I have described why we are doing this and how the services we create can look like. So now maybe more into the how part. Let's see here. So in short, to achieve our predictive maintenance systems of the future, we put a lot of confidence in data. And luckily at Scania, we have quite a lot of this data, because in 2010, I thought, but in 2011, according to this graph, we made this strategic decision to connect all the vehicles. So we have actually for a very long time collected connected operational data from our vehicles. And that's very important when you want to predict what is going on with the vehicle, knowing what it does. But it's not only because we have this much data that we put that kind of confidence in data and modern data-driven technology. It's also, I mean, we of course we see the evolution that we get more and more data and AI advancements, but also the complexity of our product. Our products are getting more and more complex with these autonomous electrified vehicles, and specialized prognostic models will also be more expensive to develop. So for that reason, we see also another reason for going the data-driven way. And there is also an urgency to be able to act fast with ever, I mean, faster and faster changing environment. So a little bit more about our data-driven strategy. Of course, we want to realize the full potential of modern tech like machine learning and AI. We are researching how we are coping or making use of this higher rate of data that we see. We are researching how we make use of our more accurate predictions to make even better maintenance planning. But that's not all. We also need the feedback loops. We need to know what we do. We need to be able to evaluate, validate, and improve our models. And that we do by observing what actually happened with our vehicles. And that we can do from workshop history data. And here I think one of our competitive advantages at Scania actually is we own our workshop network. So we actually see repairs and renewals of components much longer period than most of other makes that will need to rely on the warranty statistics that they receive. So that we need to make use of, but we also maybe need to update that as we scale up our proactive efforts. Then of course we see that the data landscape will change. We will do things more flexible. We will read out data more flexibly from the vehicle. We will be able to do it in a higher rate. We will be able to make use of these GPUs that we put on the vehicles because of the autonomy functionality to actually train and serve AI models on board compared to today. So just diving into one of the key capabilities. I think most of you are quite familiar with this. I mean, just running through, how we look at different maintenance strategies. We typically talk about 3 different strategies, where the first one is this in-service failure. We just wait until things break and then we renew them, which is not very much of a policy or strategy you could think, but it's some sort of baseline. It's very important also to estimate the potential of different preventive or proactive efforts. Then we have the preventive renewals, where we play it safe. We renew things early with a huge margin, so we make sure to avoid it. But this will also result in a lot of over-serving, which is costly for Scania and not so good for the customer as well, because when we do over-maintenance, it actually is downtime for our customers. Even though it's not a breakdown with the towing and all this replanning, it's still downtime, those extra hours they will spend in the workshop. And then we have what we are all striving for, this perfect future where we are predicting exactly when the equipment is about to fail, so we can, based on these predictions, renew them, maybe not as much or as close before they fail as in this picture, but as close as we can plan it together with the customer. And we also see this, I mean, moving closer to these actual lifetime of a component as a key driver for having a sustainable workshop operation, because if we, I mean, first of all, we maximize our customers' uptime, but we also maximize the component utilization. And if we actually manage to maximize that without going as far as breaking it, we sort of promote the potential of giving our components a second life in reuse or recirculation or other types of more sustainable waste than just scrapping it or recycling it. Yeah, so this is just a thinking model, very schematic. I mean, we direct our preventive or proactive efforts to some key components which have a very direct impact on the uptime for the customer. And for the customer, it doesn't really matter what component it is. It could be a silly small component, or it could be a really expensive complex component as a turbocharger. For them, it doesn't matter, because an interrupted transport is an interrupted transport. But from a service production cost perspective, it actually does matter. Of course, we will avoid this towing and the replanning and what I listed before. But if we would suddenly start to renew a lot of turbochargers with very low accuracy, that could be really expensive for Scania if we sell this as a contract. And I don't think a customer would want to pay for it either. So this is, I don't know if it's very visible, but this is what I wanted to illustrate here with this sort of the relation between how costly the component is and sort of the required accuracy of our predictive models. For a cheap component that is causing a lot of problems for the customer, we can be quite blunt, we can play it safe and we can renew it quite often. But for the more expensive ones, like the turbocharger, we need to be more accurate for this to make sense from a business perspective. Okay, so a little bit more practical. I see predictive maintenance as a two-step process. First, we predict when things are about to fail with minimum, error and uncertainty. And then, based on these predictions, we plan our maintenance actions in order to mitigate these unwanted consequences. And when we succeed with this, it could be a huge value for our customers. When we renew a turbocharger, it takes 2 hours, 3 hours. When we don't renew a turbocharger, but we need to do it after it has broken down, that could mean for a customer 1 or 2 lost days in operation. So it's a huge difference. And if we look a little bit more practical on how we do this, you have seen that, or I've explained that we are reaching for data, we're using data. So here you see if we could just measure the health of a component over time, that could be what we plug into the maintenance optimizer, and then we have our intervals. But unfortunately, it is not that easy. We very rarely measure health in that direct way, so we often need to rely on more indirect measurements of health, or we estimate it based on these indirect measurements. And that's not so easy. And our trucks, they can be quite different, and we read out a lot of data regarding a lot of the different aspects of the operation, so we need to choose, or we need to know what variables we should rely on. And here we see that we need an automated approach for this, because a human is not very good at deciding how should the power consumption, or the fuel consumption, the cab size, the distance between the axles all be accounted for in the model. And also, what is a similar vehicle? In terms of what, we don't do identical trucks. We customize them for our individual customers, but they are identical to some extent, and what should we focus on when we are building these models? So those are some of the challenge, but also to sort of, as I already talked about with the failures, we need to know the lifetime of our components to be able to build these estimates. And luckily at Scania we have a very good quality of our components, but that's not so lucky for building these models because we rarely see the failures, or we see just a very small part, so our data is typically very censored. So that's also something our methodology needs to address. So here I've illustrated one way that we have gone about this, which has been quite successful, where we learn from previous vehicles with the failures, and from their historical usage data and the way that they are configured, what vehicle it is, what engine, what axles. I mean, we can go into quite high resolution if we want. And then we rely on a neural network to do this sort of selection or finding the features for us. And the output of this neural network will then be what we are plugging into the maintenance planning. Sounds easy. It is not that easy because, I mean, the operational data that we read out, it's not perfect high-resolution time series because, I mean, that would be very expensive, and that would be either require a lot of memory in the onboard computers, or that a lot of data is always streamed from the vehicles. So what we typically do is that we aggregate these features or these variables, and then we read them out as histograms, which has benefits in terms of data memory, but I mean drawbacks when it comes to finding good models. Also, these categories, I've hinted that we have quite a high resolution, which could actually lead to a really, really wide data set. So even though I say that we have a lot of operational data, maybe it's not enough to sort of account for that type of dimensionality of the input data. Then also, it's not really straightforward how we output these type of functions from a neural network. So that's also another challenge to address. And what is an optimal maintenance policy? It needs to account for the cost of the different outcomes, weighing this risk of a failure to the cost of the maintenance. But at the same time also account for, I mean, we have sold this as a contract, the remaining contract, maybe we need to update the decision during the contract. So here we have a lot of help from our research partners. We have researched this area for quite some time. This was one of the first publications that at least I know about, where we started to model this problem as a sliding window problem, where we are classifying each operational readout to be either a readout that is corresponding to a failure in a certain time period or not. We also applied a cost-sensitive thresholding on the prediction, so we could actually weigh these undesirable outcomes with a higher cost, or punish the model with a higher cost. Then we have also done some research on how we address the limited failure data availability. We have it both in absolute numbers and sort of the skewness or the imbalance of the vehicle addressed in this paper, where we use a generative approach to generate synthetic data examples. And I mean, more recently, some approaches more similar to the one that I showed in the slide before here, where we are utilizing neural networks to predict these survival functions or lifetime distributions, where we both are using assumptions on the distributions in this weighable recurrent neural network approach, and where we have a more sort of relaxed requirement on that. And here also Erik is part of that publication, our share for this session. Okay, so that's about it that I wanted to talk about regarding this first capability. Now when we turn into the health monitoring part, we need to recognize this fact that we have a lot of different trucks. And knowing, I mean, we are very proud of our modular system at Scania. That's one of our claim to fame, that we can customize a vehicle to the individual customer's operation. But it's also something that is making it much, much harder for us to detect and categorize deviations or anomalies. I mean, our trucks can look very different. They could be fire trucks. They can operate in extreme environments, under the water or at construction sites, even under the surface. So one challenge that we are struggling with is this, determining if we see an anomaly or just a typical usage or a typical configuration of a vehicle. So one way that we have looked into to address this challenge, I don't know if it's animated, very nice, is with the federated approach. So in traditional machine learning, we have a very centralized approach where every data is sent to one place. We train an algorithm, and that algorithm is used on all individual units. But that approach is sort of struggling with the variability of our fleet. So where we have seen success with this federated approach is that where we're training individual model on each edge or each, sorry, this one was automated. We train the model on the edge of each truck, and we see that sometimes can handle this variability in a better way. And it also has some pros going forward with more emphasis on data privacy, that we keep our data private, we only share the weights of the model to the central location. And it could also be for some of our applications that require to be off-grid beneficial. So yeah, this plan for the stops, I think this is, what I want to underline, to get this Formula One kind of feeling for the customer when actually things go wrong, when we cannot plan for it. We need to be able to know early what to fix. Already when we get the deviation warning or when the customer calls us, we need to start the process of fixing this. And that could be for a service advisor that's receiving the customer, ensuring that the spare parts are there, ensuring that the right skill is available in the technician, etc. So for that reason, we have built this AI-powered troubleshooting tool, which is using both vehicle data and customer complaint data, textual data, describing the problems. And it's meant to assist the service advisor in knowing early on what to expect, what workshop actions are to be expected when the vehicle arrives. So I will share with you a little illustration of how that can look. So now I'm pretending to be a service advisor, and I get a call from an angry customer maybe, who has a decreased braking effect. And as I put this into the system, it immediately starts to predict what could be the reason for my problem. And as I add data, these predictions are refined. And with these predictions, I have support, and I can know what components do I need to ensure that are on the shelf when the vehicle arrives. How much time do I need to plan in the workshop schedule? So it assists me in being efficient in the workshop process. But of course, this is good. This is what's needed and will be even more needed in the future. But we are far from flawless in our predictions right now. So we see that we need more data, because we see in our feedback loop that we are constantly improving the predictive performance when we get more training examples, real world examples from the workshops. But we also recognize the fact that, working with the type of operational data that we have today and the customer complaint, that will not take us all the way. So we also need to sort of challenge what type of operational parameters are we using to reach sort of the end goal where every vehicle is already diagnosed when they reach the workshop. Yeah, so yeah, this sort of is the health monitoring process where everything starts with a customer or a vehicle complaining or sending a report to us, and then the service advisor with our support it will be more efficient in knowing early what will need to be fixed, so we can get the vehicle back on the road as quickly as possible. And we have also published a little bit around this. So this is where we have explored purely on the textual model side, where we have explored on how we should address the fact that we are a global company and that the people are writing in many different languages. So in this paper we are exploring multilingual models and also some translation work to sort of address this challenge. So if you want to read more and learn more about the thinking behind this system that is assisting the service advisor, I recommend you to read this paper. Okay, and I mean, at least when you see the film, you could think that we are done. We already have this. We can sell it, and it seems to be working perfectly. But that's not really the case. I mean, we have a lot of challenges left to be solved. In some places, we need to improve quite a lot. But I mean, in general, what I would say is our key thing for the future is that we should be able to have less error and less uncertainty in our predictions, so we can move closer to these failures and maximizing the usage of the vehicle components. And these deviation alarms that I've talked about in the health monitoring, they need to come early. They need to come maybe even earlier than the fault has arrived, so they are predictive in a sense as well. And then making use of this expected higher rate of data to have these more accurate predictions, but also to reevaluate and taking into account the new type of usage. Maybe we have sold the vehicle to a new customer, or something has changed in the operation. That needs to be accounted for when making the predictions, so we can constantly and to a high rate update our predictions. And as I talked about the feedback loops will be important. They will be also something that we need to challenge on. We cannot rely on failure data when we are scaling up proactive renewals, when we don't see any, I mean, in this ideal future, when we don't see any repairs, what should we do then? We need to find new ways, new type of feedback to rely on. And also, just to emphasize that, I mean, now I talk about predictive maintenance, I talk about prognostics and predictive maintenance decision making, but I mean, this is a capability. It's something that we can use for many more things than just for predictive maintenance. It could be, I mean, the way that we should price our spare parts. It could be an input to like a remaining useful life, informed inventory management system. It could be something that the technician can use when he gets stuck when troubleshooting. Okay, this has a low expected health, then I should start my troubleshooting in this direction. And also these lead generations when we need to, I mean, when we don't have a good contract penetration, but we still need to fill our workshops, we can call our customers and prove to our customer that we know what they need, and we can get them to our workshop that way. And then what I talked about earlier with this second life, I mean, we seek to decrease our carbon footprint even more with having a circular business model where we recircle our spare parts and reuse them, and determining between what could be reused, what could be refurbished, what should be remanufactured, or what could only be recycled because of the limited health of the component. That we can use our predictions as well. At least when we sort of select the vehicles to do this for. Okay, so now I talked about the two capabilities. Now more in general, I want to underline the importance of collaboration in this field, because predictive maintenance is an interdisciplinary field. So of course we need to collaborate internally at Scania. It's not only data, definitely not. We have a lot of engineering know-how. There is obviously business aspects to this as well. And we also need to partner up to cope with this high pace of things. And that we do at Scania. We have partnered with Swedish and international top universities, where some of the researchers are in the audience today. But this is not where it ends. We are even more bold in our collaborative efforts. And what I mean then is that we have taken a bold step of sharing data. We have actually shared real-world data that we hope should spark new innovation and new collaboration and sort of in the community getting up there, I mean, see our problems and get inspired. So we have released a data set that we call Component X, and that is because for ISEC reasons we don't want to reveal what component it is, but it is one of these components that I've talked about, a high impact component that will cause a lot of disruptions for the customer if they fail. And the data set that we have compiled is quite typical for these challenges that I described. We have the no direct health measurements, so we need to sort of rely on these indirect measurements instead. We have a sequence of operational readouts that is irregularly sampled because of limited connectivity, because of other reasons of the data contracts that the vehicle run on. Even though we have higher frequency data as well, we haven't included here because this is quite typical for many of our components where we need to rely on this aggregated feature and histogram data. I think I have, yeah, this is the operational data. And we also have categories. This is only a subset of all the categories, but some of them will have an effect, and how we should model that and how we should include that in a model, that is still to be researched. And then, of course, as all our problems is quite imbalanced, we see mostly that they are not repaired, these components, within the study period that we observe the vehicles. So see this as an open invitation to connect and to collaborate. Scan this QR code if you want to learn more about it. There is a paper published describing the data more in detail than what I did. There is also an associated challenge where you should develop your own health estimation model and also a way of evaluating this, which I will not go into detail, but this sort of cost matrix that we have defined is sort of catching the fact that we are, I mean, making a much higher punishment to missing failures than doing some of these over repairs. And there is also some sort of time scale here where we are taking account how much of your prediction was as well. So I really encourage you to look up this data. So that was all what I had for today. I hope I've, underlined the importance for uptime in the truck and bus business now and in the future, and also made it very clear that we see that the way forward here is data and collaboration. Thank you.
So, are there any questions to Olaf? I will just come to you if you raise your hand, and you don't need to come forward. We offer free drinks for questions. Here you go.
Hello, thank you very much for nice presentation, very inspiring. I would like to ask you, you mentioned about predicting failures and what we can do. And you had a slide where we showed the truck under, it was under the earth, let's say, and there was anomaly, faults, and failure. Okay, do you do something before the failure? I mean, to have a fault-tolerant control that we hear a lot in this conference, or fault diagnosis. I mean. And use this information, utilize this information for the maintenance.
Yeah, I mean, we do a lot of things, but we don't do it for everything. And I think what I wanted to cover was that sort of the general problem that we have. Of course, in some scenarios, it's possible to detect things earlier before they get into failure. We have some predictive alarms as well. But in most scenarios, what the customer needs to know is not, of course, for the technician and for the workshop, it's very good knowledge, but the basic question is, can I or can I not fulfill my transport mission when the light is lit in the ICL of the truck? But yeah, there are different systems with more or less sensors, which gives us more or less capabilities of doing this, which is a very fluffy answer to a question, but it's also not one answer to it.
Any more questions?
Thank you for this interesting talk. You spoke about using neural networks in your solution. Which kind of network architectures are you using primarily? Maybe you could you elaborate on this a bit more?
I don't think I can elaborate on that actually, but we are exploring different ways, and I think that could be one key to future success, to really find the optimal way of handling this problem. So a challenge for you maybe.
Yes, hi. Thank you for the very nice presentation. I would like to know whether you do also testing and not only monitoring, taking the measures as they come.
I think, if I understand your question correctly, instead of just, waiting to things fail, if we do testing as well during the workshop visits and the maintenance, for example.
Or during the
development, maybe.
The operation of the trucks.
The operation. Trucks are coming to the workshop quite frequently. It's not like a personal car. They come every third month to the workshop on average. So yes, we do that. How we should make use of that to make our models even better, I think that's one of the open questions, but that's also one of the main hypotheses when we talk about that we need to sort of rely on something else than just these failures, the blunt binary feedback that we maybe rely too much on today.
Okay, thank you.
More questions? Then I have one. Oh, I'm hearing myself.
I need to stand right here.
Yeah. So, from my understanding, you collected data since 2010, right? So you all have all the data and you come up with the models. And then you mentioned there are new technology introduced batteries and stuff. So can you comment on how difficult it is that your data itself is highly dynamical, right? So it changes because of you have different technologies coming in, and you need to adapt your data set and your predictions.
Yeah.
And what's the time frame of, say, you put in a new battery system, and how fast can you have enough data to do the predictive maintenance?
I think that's a process challenge, I would say, because it's not about just that the technology is going fast. We also constantly updating the components in the driveline. So we need to have. Our vision is that we should have the best maintenance program in the world from day one, and that's not. Maybe accounting for the time it takes to collect a huge amount of failure data. So that's a challenge, and I think there we need to sort of make sure that we can make use of the data that we collect during the development as well. So it's not, even though that we have on-point, very useful data collected from the field, we also collect a lot of data during the development process of these products. So sort of having this smooth transition maybe between the methods that we use during the lifetime of a component, I think that's the key to success there.
Okay. Yes.
Thanks very much for this interesting talk. I think if I understand the mission of your company is to deliver the goods to the customer, right? And what you talk about is the maintenance and the monitoring to make sure that the machine do this, perform this mission is in the top shape. What and I echo you, for we run the company, it's very difficult to get the failure data. I work with a nuclear power plant. We try to get the failure data. It's just the operating perfectly. You don't get this data for machine learning.
That sounds worrying that you're waiting for that.
I know, it's waiting for that for a long time. It's never occurs. But my question to you is, to make this mission accomplished, not only just the machines, the trucks, but also the operation, for example, the weather, the traffic conditions, so on, this operation aspect. Has your company integrated the monitoring of the trucks or the status of trucks with the operational aspect of the company? If there's a landslide or this winter snowstorm coming and so on, so this is to achieve the mission.
Yeah, so I mean, as I interpret, I mean, we do transport, and we don't only do like the machines themselves. I mean, we are transitioning our company towards being a service provider, and the first step is to be able to deliver value-based selling with these uptime services. Of course, maybe the sort of ambition doesn't end there. I mean, if we would sell not uptime as a service, but transport as a service, then we would be the customer and the service provider, sort of the one paying for the service as well. So then it would, I mean, be even more crucial for us to get these things sorted. But I mean, integrating and combining and using all this data that you mentioned. Yes, of course, that's the ambition, but you need to start somewhere. There is more than 1,000 different components in a truck, and we have many different types of trucks. So I mean, what you're getting at, I think, is partly there, partly also for the future to decide if it's worth it, basically, to integrate those other types of data into the modeling. Yes.
Thank you for the very nice presentation. As far as I understood, you're using data, I mean, you're trying to correlate data with failures, with faults. I was wondering if you're also using causal models to see what is causing the fault, because you have a lot of data. So if you have gone beyond just correlation to actually look at causal models.
We have a PhD project in this area. I think that's the only thing I know about that. It's not really for me to answer. It's not the main way of doing it right now. I mean, we are mostly about just avoiding these things rather than explaining them. But of course, that could be very useful feedback data for the R&D to know as well.
I have a question, something on the same lines of one of the previous questions. So you are having a fleet of trucks. Does it lead to the problem of transfer learning, that is, transferring the knowledge acquired from a set of trucks or set of systems, and be able to generalize it with respect to fleet? So are you looking at transfer learning approaches, or does it make sense in this context? And a follow-up to that would be, you also mentioned neural networks. And so are you able to, let's say, guarantee safety or let's say, some properties given the implication of neural networks? Because, you can have divergence and so on and so forth. So my question would be, I guess, what kind of complexity is being brought by the fleet? And secondly, how useful or dangerous is the use of neural networks in this context?
Yeah, I mean, starting with the second question, I think that was one of the sort of things that really inspired me to start at Scania, working with the service business, because I mean, people do not maybe die if we don't preventively replace a turbo, except in this extreme medicine transporter case. But we can actually, I mean, we have a baseline here, which is that we haven't really maintained these components. So everything that we do is rather over maintenance than anything else. So I wouldn't say that a bad prediction is actually causing any harm compared to as of today. So I mean, that was what's inspiring, that you can actually test and improve. It might cost a little bit for Scania, but it's not worse than that. The second question, I mean, transfer learning, I'm not really perfectly informed with the definition of that, but for me it is what I described with the federated approach. I mean, that's one type of transfer learning where you train this individualized model and you sort of sum up the weights. There are of course other approaches as well, more like from computer vision inspired approaches. That might be something.
Okay, last chance. Okay, if not, I would say we thank Olaf again. Thank you. And thereby we close the keynote.
Mi senti? Sì. Ehi, ok.
Good afternoon, everyone. I have the honor and pleasure to give you an overview of the subject of my
Marco,
presentation
alza un
is
po' il volume
enhancing fault detection in
del
nonlinear
PC.
industrial processes, a reduced kernel principal component analysis-based spectral clustering approach.
Ok, aspetta un attimo che ce ne sono degli
Plan is
altri.
formed of 4 parts. My first point concerning an introduction. Second, I would like to present our proposed methodology. Next, I will discuss and evaluate our simulation results. And finally, I will end with conclusions. In modern industrial processes, ensuring operational safety, stability, and efficiency is a critical challenge. To address this challenge, several data-driven techniques have been developed to analyze complex process data and detect anomalies and indicators of faults. Principal component analysis is a widely used data-driven technique that reduces the dimensionality
It's my great honor to attend this conference. My title is Novel Manifold Autoencoder and its application to industrial fault diagnosis.
Good afternoon, everyone. I have the honor and pleasure to give you an overview of the subject of my presentation is enhancing fault detection in nonlinear industrial processes, a reduced kernel principal component analysis-based spectral clustering approach. Plan is formed of 4 parts. My first point concerning an introduction. Second, I would like to present our proposed methodology. Next, I will discuss and evaluate our simulation results. And finally, I will end with conclusions. In modern industrial processes, ensuring operational safety, stability, and efficiency is a critical challenge. Hello everyone, and thank you for being here. Today I will be talking about our research on genetic algorithm-based hyperparameter optimization of deep learning for fault diagnosis. In this presentation, we will cover several important parts of our research. First, we will talk about the background and motivation for our study. Second, we will give an overview of deep learning and genetic algorithms. Hello, everyone. Good afternoon, everyone. I have the honor and pleasure to give you an overview of the subject of my presentation is enhancing
It's my great honor to. We will.
No, devo andare in regia, un secondo.
So thanks to be here to this session of artificial neural networks for diagnosis. So I'm Mirko Mazzolini from University of Bergamo. I'm with my colleague Mohan Jardiri. We'll co-chair this session. So the first presentation is actually a recorded video. The title is Novel Manifold Autoencoder and its Application to Industrial Fault Diagnosis. Okay, so let's start.
It's my great honor to attend this conference. My title is Novel Manifold Autoencoder and its Application to Industrial Fault Diagnosis. We will introduce the content of this paper from the following 5 aspects. They are background, limitation of SAE in fault diagnosis, ULSAE feature extraction algorithm, experimental results, and the conclusion. Safety accidents have significant impacts. In March 2019, an extremely serious explosion in Jiangsu province caused 78 deaths, 76 injured, with a direct loss of 1.986 billion yuan. In February 2023, an extremely serious collapse in an open pit coal in Inner Mongolia led to 53 deaths and 6 injured. Now, ensure safety production has become an inevitable topic. Model industry process for diagnosis is difficult. This is due to several key reasons, include increasing complexity, large volume of data, real-time diagnostic requirements. These facts make it challenging for traditional fault diagnosis methods to achieve satisfactory results. The rise of technologies such as machine learning. In recent years, machine learning technologies, especially deep learning technologies, have achieved remarkable achievements. The widespread use of industrial sensors has enriched the industrial fault data. Consequently, machine learning algorithms have attracted the increasing attention in the field of fault diagnosis. The picture is the explosion accidents in Jiangsu province. And this is the number of accidents and the number of deaths in China of every year. This picture introduce the structure of the SAE. We can see that it includes encoder and decoder. At the training time, the construction loss is minimized. There are many advantages of SAE, include no linear feature learning. SAE can learn complex non-linear feature which linear method might not capture. And SAE is simple. The basic structure of SAE is relatively simple, which makes it easier to understand and implement. Besides, SAE has more efficiency. When used as a feature extractor, SAE can improve the efficiency of machine learning tasks. Although SAE has many advantages, but it still has some limitations in the field of fault diagnosis. First, the overlap of different classes in the dates affect the training efficiency. So, we should remove the overlap samples. And SAE trained to overfit during actual training affect the robustness of SAE. So, in this paper, we use a spell autoencoder to solve this problem. And the feature extracted by SAE have a random projection problem and can probably adapt to the requirement of classification tasks. So, to solve this problem, we combine the SAE with supervised learning method, LDA. This picture shows the structure of fault diagnosis based on ULSAE. The ULSAE have three parts. They are undersampling parts, feature extraction parts, feature classification parts. And we will introduce this part. First, undersampling parts. If a sample points contain many samples of the same classes around it, we consider it as a core point and save it. If a sample point contains many points of different classes, we consider it as a maxed point and delete it. Undersampling is done in this way. And we can see from the picture, show the process. Second class, LDA principle. As we can see, the D is the training dataset, where each sample Xi is an n-dimensional vector, and Y is a neighbor. Xj as a set of samples in the J classes. U as a mean factor of the samples in the J classes. Because LDA requires maximizing the distance between the classes' center of different categories. At the same time, we hope that the projected point of simple category of dates are as close as possible. Therefore, it's necessary to optimize the funnel function. And then, we generally define the inter-class scatter metric SW as follows in this function. And then, we define the inter-class scatter matrix SD as this. By maximizing the expression J, we can achieve the two-dimensional LDA. This picture is the result plot of the LDA. Like LDA algorithm, LSAE also defined inter-class scatter and inter-class scatter. They are function 2 and function 5. Unlike LDA, LSAE swap the position of SW and SD. The projective function changed from maximization to minimization. The loss function of LSAE is presented by the funnel function as said. And the four classification parts. The implementation principle of the KNN. In order to determine the category of an unknown sample, all unknown samples are used as reference points. The distance between the unknown sample and all known sample is calculated, and the k nearest known sample are selected based on the distance from the unknown sample. To determine the category to which the sample belongs, based on the category of majority of k nearest neighbors. And this picture is the KN principle. Show the KN principle. In these experiments, we use the TEP datasets. The TEP dataset includes 52 variables for each sample and cover the total of 21 different types of boards. This allows the TEP dataset to very realistically simulate real industry conditions and have been widely applied in many fields. In this experiment, we select 4 data of type 3, 4, 9, 11, 14 for study and analysis. This is the experimental results of the TE datasets. The chart illustrates the accuracy of fault diagnosis using variable feature extraction algorithm across different output dimensions. The experimental results indicate that ULSAE has the highest classification accuracy, demonstrating the best feature extraction performance. Besides, from this table, we can see that ULSAE have the lowest dimension and the lowest AIC value, which shows that the ULSAE has the best performance. This page shows the heat map of accuracy with different kind of feature extraction algorithm. And we can see that the ULSE have the best performance than other algorithms. So, in this conclusion, this article starts from a field problem of disadvantage between SAE and the traditional algorithms, and proposed the ULSAE algorithm that combined SAE and LDA to enhance the generalizability of the mode. The ULSAE algorithm employed a subsampling method based on the overlap degree, efficiently improving the performance of the algorithm. Experimental results on the datasets with strong non-linearity in TP dataset show that ULSAE algorithms have improved for diagnosis accuracy, reduced data dimensionality, and performance outperformance algorithms such as PCA, LDA, and LPP. So this is our report. Thank you for your attention.
Okay, so let's thank our virtual speaker. Is there someone in the room that can answer questions to our virtual speaker? Okay, so if not, I think we can move to the second speaker of this session. Okay. Let me open the presentation. Okay, you have a pointer here if you would like. So, our second speaker is Mouad Bougoufa. It will present a work entitled Stacked Autoencoder-Based Diagnosis Applied on a Solar Photovoltaic System. So, please.
So, good afternoon, everyone. It's my pleasure to stand before you today to present significant advancement in renewable energy technology, particularly in the domain of photovoltaic systems, titled Stacked Autoencoder-Based Diagnosis Applied on Solar Photovoltaic System. So, our presentation explores cutting-edge approach, employing stacked autoencoder for fault diagnosis in PV systems. The presentation is structured part with truthful introduction into the domain of photovoltaic systems. We'll proceed by the objectives that guide our research, and secondly, the methodology section that will detail the approach, tools, and techniques, results, and will conclude with insightful conclusion. Recent years have witnessed significant advancement in renewable energy, especially in solar power via photovoltaic systems, contributing to the global shift toward sustainability. These systems face challenges associated with faults that can affect their reliability and performance. Traditional methods lack the complexity needed for comprehensive fault detection in these dynamic systems. To address the complexity of fault detection in PV systems, development of advanced artificial intelligence techniques has become increasingly important. These advancements showcase the potential of inventive strategies in identifying faults within solar energy systems, emphasizing the need for improved fault detection methodologies. In this presentation, we will introduce an effective solution to this challenge. Our proposed method consists the use of stacked autoencoder neural network and the mean square error for fault detection. Our research is driven by a set of clear and ambitious objectives, each designed to address the challenge of fault detection in PV systems by employing the power of AI techniques. Firstly, create detailed model parameters, enabling precise simulation of PV system behavior. Secondly, employ historical data from the PV array in effective manner to address the critical task of fault detection within these systems. And lastly, develop an advancement fault detection methodology adapted specially or specifically for solar photovoltaic system. For the methodology, we start with the system modeling. The system considered in this study is shown in figure 1, which consists of PV array models, DC-DC boost converter, maximum power point to control our output like current and voltage, inverter to convert direct current to alternative current, and sensors. So, the electrical characteristics of the PV system are non-linear characteristics and have just a single maximum point as appear in figure 2. The IV curve of the PV model passes through three important, which are the short circuit current, the open circuit voltage, and the maximum power operated at maximum voltage and maximum current. The typical IV characteristic curve of the PV system used under standard test condition, where the irradiation equal to 100 watt per meter square and the temperature equal to 25 degrees Celsius. So, our suggested approach for fault detection in PV systems involves several case steps. First, utilize MATLAB simmering for gathering and refining datasets. Then, the datasets encompasses healthy and faulty condition. So we have two scenarios, healthy scenario and faulty scenario, focusing on the series resistance faults. For fault detection, we used staked autoencoder model. The staked autoencoder model is trained using the pre-processed data to generate and estimate output. The trained model is then validated and optimized to minimize the output reconstructed error. The learning process needs to estimate the parameter by employing the mean square error method. Figure 3 summarizes the flow chart of this proposed method as we explained previously. As a neural network that attempts to reproduce the input as identical as possible, the architecture and the schematic diagram of standard autoencoder is the effective algorithm to learn representation from the healthy monitoring data and recognizing the healthy status. So, our autoencoder is shown in figure 4, which consists of input layer, is the encoder layer, and output layer is decoder layer or the estimate output, and the hidden layer referred to as the bottleneck layer. The staked autoencoder is deep learning neural network that uses the power of future learning by employing layered architecture. Multiple layers of autoencoder are sequentially staked. For example, the first autoencoder, the hidden layer or the bottleneck layer of the first autoencoder is the input of the second autoencoder. And like this, to have sequentially staked autoencoder, as shown in figure 4, of course. And the method likely relies on analyzing residual between the staked autoencoder output and the actual data to detect anomaly indicative of faults. As a schematic diagram, figure 6b explain the error between the input X and the estimated X. Once the estimation output phases have concluded, the mean square error function is used to test the construction accuracy for the original attribute for cost function as follows. We have the number of the data point, and the xi is the actual data or the observed data, and the estimate x is the predicted data or the estimated data. The specific test database for the staked autoencoder is based on the mean square error between the input and its reconstruction in the output results. The MATLAB Simulink-based simulation of EV and PV curve characteristic under varied fault condition, utilizing data from PV models. We specifically focused on the SunPower SPR model as a reference. The simulation aimed to construct the performance between the healthy state and the series resistance fault scenario. So, two primary scenarios were simulated. The first one is the healthy state. The simulation ran under standard test condition, aimed to capture the EV and the PV curve characteristic of the PV panel system when functioning optimally. And the second scenario is the faulty state. For us, it's the series resistance fault. A fault condition was introduced in the simulation to mimic the series resistance degradation scenario, wherein the performance of the PV system deviates from its normal operating state. As we see here, the knee of the curve. The blue one is the healthy state, and the red one is an augmentation or increase in the series resistance, and the yellow one is the degradation, the second degradation of the series resistance. This part here and this part here for IV curve and PV curve. The residual between the staked autoencoder output and the actual data detect anomaly indicative of faults. So the mean square error analysis shows low value in the healthy state and the noticeable increase after introducing a fault between 400 samples and 700 samples, indicating the model adaptability and effectiveness in fault detection. Conclusion. In conclusion, this study has represented a comprehensive exploration into fault detection within photovoltaic systems using staked autoencoder neural network. The implementation of the staked autoencoder for dynamic fault diagnosis in PV systems has yielded successful results. And the system can accurately detect faults. The fault detection illustrated in Figure 7 demonstrate the effectiveness and potential of staked autoencoder in improving the reliability and efficiency of the PV systems. So there is some reference that we used to write our paper. And thank you for your attention.
Okay, thanks for your presentations. Any questions from the audience?
Is there any questions?
Okay, maybe I will start with one in the meanwhile. So if I understood correctly, you generated your data using Simulink or a modeling software like this. Do you consider also the addition of noise to your data, or you simulated data without noise on the measurements?
No, I didn't take in consideration the noises.
Mm-hmm. Do you think it will affect in some way the learning of your autoencoder model, or do you think it is a robust model?
Now it will be the same because the stake autoencoder will give us the estimation output. So the noise will not do so.
Okay, thanks. Other questions?
Another question? Okay, I have one question. In the previous presentation, the student preceded the stacked autoencoder by a feature extraction and selection algorithm. In your case, you used directly the stacked autoencoders. Is it necessary to precede the stacked autoencoders by feature selection and extraction and selection algorithm, or the stacked autoencoder can do this task itself?
The autoencoder can give us results, but with the staked autoencoder it will give us much better results, much better estimation output. That's it.
Another question? Okay, thank you, Matt, for this presentation.
Okay, so next we have another video. In the meanwhile, I ask if presenter number 4 and 6 are here in the room to show up. Okay, so let me start the video. Okay, so next presentation is entitled Enhancing Fault Detection in Nonlinear Industrial Processes, a reduced kernel principal component analysis-based spectral clustering approach.
Good afternoon, everyone. I have the honor and pleasure to give you an overview of the subject of my presentation is Enhancing Fault Detection in Nonlinear Industrial Processes, a reduced kernel principal component analysis-based spectral clustering approach. Our plan is formed of 4 parts. My first point concerning an introduction. Second, I would like to present our proposed methodology. Next, I will discuss and evaluate our simulation results, and finally, I will end with conclusions. In modern industrial processes, ensuring operational safety, stability, and efficiency is a critical challenge. To address this challenge, several data-driven techniques have been developed to analyze complex process data and detect anomalies and decay of faults. Principal component analysis is a widely used data-driven technique that reduces the dimensionality of high-dimensional data by extracting the most informative features. However, the traditional PCA method is not suitable in nonlinear cases and assumes that the relationships between variables are linear. Hence, it may not be able to tackle the issue of nonlinearity to a great extent and thereby not always be the most appropriate method of analysis. To overcome this limitation, kernel principal component analysis is the most popular technique that attracts a lot of researchers and has gained potential attention as a nonlinear extension of PCA, providing a more adept tool for monitoring nonlinear processes. Despite kernel PCA offers a robust solution to handle nonlinear data, its computational requirements are a significant issue, especially for large-sized datasets. In this context, a reduced KPCA technique is developed to efficiently reduce the size of a training dataset by retaining the more relevant observations, thereby addressing the computational and storage challenges associated with the conventional KPCA-based fault detection scheme. The developed reduced KPCA is based on spectral clustering, which represents a powerful technique that leverages the spectral properties of matrices derived from data similarity measures. The basis of spectral clustering lies in transforming the data into a new representation in which the underlying structures are more prominent. It does this by constructing an affinity matrix that encodes pairwise similarities or dissimilarities between observations. The main steps of the evolved approach are illustrated as follows. First, An affinity or similarity matrix is created to represent the relationships between data points. This matrix captures how similar or dissimilar data points pairs are. Second, from the affinity matrix, the Laplacian matrix is computed. This matrix encodes the relationships between data points and their centers to the spectral clustering process. Next, the eigenvectors of the Laplacian matrix are computed. These eigenvectors capture the structure of the data in the spectral space. Then, often only the first few eigenvectors are used for clustering, providing a dimensionality reduction while retaining the most important information. Lastly, traditional clustering methods such as k-means clustering are applied to the transformed data in the spectral space where clusters are generally more separable. Now, I would like to bring your attention to our simulation results. The developed approach is applied to a Tennessee-Eastman process, which is a widely used benchmark process in the field of chemical engineering for testing and developing control strategies, fault detection methods, and process monitoring techniques. The process consists of 8 components. J and H are the main products. A, C, D, and E are reactants. F is a byproduct, and B is an inert component. It also consists of 5 main units: a reactor, a condenser, a recycle compressor, separator, and a striper, as displayed in the corresponding figure. The Tennessee-Eastman benchmark simulates 21 different faults, and their descriptions are given in the following table. The effectiveness of the proposed method is evaluated through key performance metrics, including false alarm rate, which represents the false alarm rate defined by the probability that a given fault index surpasses its corresponding threshold, knowing that no fault has already occurred. Missed detection rate, which is the probability that a given fault index does not exceed its corresponding threshold, knowing that a fault has already occurred. Detection time delay, which represents the elapsed time between the detection and occurrence of a fault. Gained execution time is depicted as the following equation 1, where ETR represents the execution time through a reduced dataset, and ETL represents the execution time through the original dataset. Gained storage space is depicted in equation 2, where SSL represents the occupied space by the kernel matrix of the original dataset, and SSR represents the occupied space by the kernel matrix of the reduced dataset. And loss function, which is performed and determined by, in terms of the 3 monitoring indicators FIR, MDR, and DTG, as follows, where the desired values for FIR, MDR, and DTG are fixed at 5%, and 1 sample in this study. The following figures illustrate the monitoring results in fault IDV1 using the various fault detection indices established by the conventional KPCA and the proposed reduced KPCA paradigm. The monitoring performances and computation time obtained using the classical KPCA technique and the developed approach are reported in the following tables. The spectral clustering techniques generated a new training dataset with size equal to 800 instead of the original size, which is equal to 1024. And it decreases the computation time of the conventional KPCA from 5.01 seconds to 1.61 seconds. Consequently, it gains 38.96% and 67.86% of the storage space and execution time, respectively. Besides, 3 loss functions, including JT squared, JQ, and JPhi are computed, and their average is obtained to evaluate the performance of the proposed reduced KPCA paradigm compared to the conventional KPCA, as displayed in the following figure. These outcomes demonstrate that, in comparison to the conventional KPCA technique, our developed scheme contributes to adequate and acceptable loss function values. Moreover, the KPCA method requires a round of 8.4 times 10 to the power of 6 bytes of memory storage, whereas the suggested reduced KPCA-based spectral clustering methodology requires only 5.12 times 10 to the power of 6 bytes of storage space. Thus, according to the other results obtained, we can conclude that the reduction of the dataset not only improved the time and space computations, but also may lead the monitoring algorithm to converge to better performance. Finally, we can recap our main points in this conclusion. This study addresses the critical need for enhanced fault detection methodologies in nonlinear and serial processes, focusing on the Tennessee-Eastman process as a representative case. Our proposed approach, integrating reduced kernel principal component analysis-based spectral clustering, stands as a promising solution to resolve the computational demands of KPCA with the complexities of nonlinear data. By strategically reducing dataset size during model training, our method not only streamlines computational burdens, but also preserves the most relevant features, addressing the challenges of handling large-scale industrial datasets. The experimental evaluation considering K-metrics, including false alarm rate, missed detection rate, detection time delay, computation time, execution time, and storage space, demonstrates the efficacy of our approach in enhancing fault detection capabilities, thereby showcasing its potential to overcome the limitations of traditional fault detection methods. Thanks for your attention.
Okay, thanks our virtual presenter. Again, is there someone in the room that might answer questions related to this talk? Okay, I think no. So I ask if presenter number 4 is here in the room or not. Okay, so I think we have to wait half an hour for presenter number 5, which is, however, online.
We have so half hour of waiting before the 5th presentation. We have to respect the timing.
Presenter number 6 is here. Okay, so we have the last presenter. he will present genetic algorithm-based hyperparameter optimization of deep learning for fault diagnosis.
Hello everyone, and thank you for being here. Today I will be talking about our research on genetic algorithm-based hyperparameter optimization of deep learning for fault diagnosis. In this presentation, we will cover several important parts of our research. First, we will talk about the background and motivation for our study. Second, we will give an overview of deep learning and genetic algorithms. Then, we will explain our method for hyperparameter optimization and how we use it. After that, we will discuss the experimental setup and the results we found. Finally, we will summarize our findings. Let's begin with the background and motivation behind our study. Renewable energy sources, especially solar energy, have gained significant traction globally to their potential to provide sustainable and environmentally friendly energy. Grid-connected photovoltaic GCPV systems have emerged as prominent solutions in this domain. However, the reliability and efficiency of these systems are often compromised by various types of faults. Effective fault detection and diagnosis are therefore essential to maintain the performance and extend the lifespan of the GCPV system. Fault detection and diagnosis in GCPV systems are crucial for preventing performance degradation and ensuring safety. Common faults including open circuits, short circuits, and degradation of photovoltaic modules, which can lead to significant energy losses and safety hazards. In PV systems, the produced PV power depends on various factors such as the nominal characteristics of the compounds, the power electronics interface, the weather conditions, and fire that may occur in the different stages during the operation. In our research, we focus on improving the accuracy and reliability of fault detection in these systems using advanced techniques like genetic algorithms and deep learning. Let's delve deeper into the overview of these technologies and how they can be applied to this problem. Recent advancements in deep learning have revolutionized fault detection and diagnosis in grid-connected photovoltaic systems. Techniques such as artificial neural network, recurrent neural network, and long-term memory have shown superior accuracy and robustness compared to traditional methods. This is largely to their ability to learn and recognize complex patterns from large datasets, which is crucial for effective fault detection and diagnosis. On the other hand, genetic algorithms are a powerful optimization techniques inspired by the process of natural selection. Genetic algorithms are particularly useful for hyperparameter optimization in deep learning models because of their ability to perform a global search and avoid local optima. Artificial neural networks are the basic building blocks of deep learning, commonly utilized for tasks like classification. They consist of interconnected nodes or neurons organized in layers. Each neuron receives input, processes it using a mathematical function, and passes the output to the next layer of neurons as shown in this figure. ANN are able of learning complex models and relationships from data through a process called backpropagation, where the network adjusts its internal parameters to minimize prediction errors. Moving on from artificial neural networks, let's explore recurrent neural networks, which are especially designed to handle sequential data. Unlike traditional feedward neural networks, RNN processes internal memory states, enabling them to capture temporal dependencies in data and excel in tasks like time series prediction. Let's delve into long short-term memory networks. A specialized type of recurrent neural network, LSTM, are designed to tackle a common issue faced by traditional RNN known as the vanishing gradient problem, especially when dealing with lengthy sequences. This by incorporating unique mechanisms like memory cells and gating units, which enable them to selectively retain information over time. This adaptive approach allows LSTM to effectively capture long-range dependencies in sequential data, making them indispensable for tasks demanding context modeling over extended time periods. Genetic algorithms are optimization algorithms inspired by the process of natural selection and genetic evaluation. In a genetic algorithm, a population of potential solutions evolves over successive generations through processes such as selection, crossover, and mutation. By evaluating the fitness of each solution according to a predefined objective function, genetic algorithm can be effectively search large solution spaces for optimal or near optimal solution. So in the context of deep learning, genetic algorithms are often used for hyperparameter optimization, where they explore different combinations of model parameters to find configurations that minimize performance on a given task. Moving on to our proposed methodologies, we'll delve into how we integrate these two powerful approaches for hyperparameter optimization. Hyperparameter tuning involves selecting the best set of hyperparameters for a learning algorithm. A hyperparameter is a model argument whose value is set before the learning process begins. The success of deep learning algorithms heavily depends on effective hyperparameter tuning. Examples of hyperparameter include the number of layers, the number of units per layer in a neural network. As shown in the figure, model parameters are learning from data, while hyperparameters are tuned to achieve the best performance. Searching for the best hyperparameters can be choose and complex. That's why we use search algorithms like genetic algorithms to streamline this process. Let's talk about integrating genetic algorithms with deep learning techniques for hyperparameter tuning. Here is how it works. First, we split and pre-process the PV dataset into training and testing sets. This ensures our model has separate data from learning and evaluation. Next, we define the structure of our deep learning model and specify the ranges for hyperparameter we want to tune. These hyperparameters can include the number of layers, learning rate, and batches. An initial population of possible hyperparameter configurations is then generated. Each configuration represents a unique set of values within the specified ranges. We train the model with each configuration, evaluate its performance, and calculate fitness scores. The scores help us determine how well each configuration performs. Top performing configurations are selected to form a matching pool. For this pool, new configurations are created through the crossover and mutation, generating a new population. This process of evaluation, selection, crossover, and mutation is repeated for several generations. Each iteration helps refine the hyperparameter, improving model performance. Finally, the best set of hyperparameters is identified. We train and test the final model using these optimal settings, ensuring the highest possible performance. This approach automates hyperparameter tuning, making it far more efficient and enhancing the performance and adaptability of our fault diagnosis method. Having outlined of proposed methodologies, let's now move on to discuss the results and the insights we've gained from our approach. In our work, we used PV and grid emulators to replicate the operation of the PV panels and a three-phase grid as shown in the schematic. We introduced faults at various points, including the common coupling points, inverter sensors, and PV arrays. Multiple sensors were placed to collect data from key points in the system. This setup allowed us to thoroughly test our fault diagnosis method in different scenarios and gather comprehensive data for training and testing our models. Our resulting dataset comprises 9 variables with the duration of data recording varying between 5 to 10 seconds. The recording duration depends on the type of fault being investigated and the potential damage associated with each injected fault in the system. Next, let's discuss the specific faults we investigated in our GCPV system, characterized into grid-side and PV-side faults. These faults were systematically introduced to evaluate the robustness and accuracy of our fault detection methods. Each type of fault presents a unique challenge and helps us understand the system behavior under different field conditions. Furthermore, our fault diagnosis system involves constructing a database with classes C0 to C5, representing healthy and various faulty states. We allocated 60% of the data for training purposes, ensuring our model learns. The remaining 40% of the data were received for testing. Moving forward, let's take a closer look at the algorithmic parameters utilized in optimizing hyperparameters for deep learning techniques such as NN, RNN, and LSTM through the genetic algorithm. The genetic algorithm operating with a population size of 10 individuals and iterated through 10 generations. During each generation, the accuracy of individuals was evaluated to determine their fitness for the selection process. Comparing the performance without optimization to that with the genetic algorithm optimization reveals significant improvements across. For instance, without optimization, NN achieved an accuracy of 92.45%, while with genetic algorithm optimization, accuracy increased to 94.51%. Therefore, RNN without optimization showed an specified performance, but with the genetic algorithm optimization, accuracy reached 97.53%. Notably, LSTM exhibits lower accuracy without optimization at 96.03%, but with the genetic algorithm optimization, accuracy surged to 97.57%. These findings underscore the crucial role of hyperparameter optimization in enhancing the performance of deep learning models, contributing to more accurate fault diagnosis in GCPV systems. Let's look at the confusion matrix for the long short-term memory model during testing. In the healthy samples category, 4,553 out of 4,800 samples were correctly identified, with a precision of 91.22% and recall of 94.85%. However, there were challenges in identifying all samples in other faulty categories. Despite perfect identification for samples in some classes, these metrics give us insight into how well the LSTM model performs in diagnosing faults. Let's move to draw some conclusions from our findings. In our study, we focused on ensuring the reliability of grid-connected photovoltaic systems. For fault detection and diagnosis, by addressing potential issues, we can maintain the optimal performance of these systems. To achieve this, we use deep learning techniques to classify the various operating modes within the GCPV system. This approach allows for the accurate identification of deviation and faults, ensuring that any anomalies are detected. Furthermore, we incorporated genetic algorithm to fine-tune for the hyperparameter of our deep learning models. This optimization process significantly enhances the performance of these models, leading to improved fault detection accuracy. Our simulation results highlight the robustness and effectiveness of these proposed methodologies. The findings clearly showcase the ability of our approaches to detect and diagnose faults, thereby ensuring the efficiency of GCPV systems. Thank you for your attention.
Okay, so let's thank our virtual speaker. Is there anyone in the room that would like to ask, or not to ask, to answer some questions for the presenter? Okay, seems there are no one. Okay, we are a bit ahead of a schedule. I think we might wait maybe 2 minutes.
We have 5 minutes more to ask a question. I have a question to ask and a comment to give about the genetic algorithm, which are a powerful optimization algorithm, but he has, as the most of the existing algorithm, some limits. One of these limits is the local optimum. When we use genetic algorithms, there is a risk to reach a local optimum and not global or optimum. I think in this work, before using the genetic algorithm, there is another parameter identification technique that is used, and the genetic algorithm are used also to increase this, the accuracy. This can allow to avoid these local optimums, in my thinking. And maybe the student in her paper gives more details on this point.
Thanks for your contribution. Okay, so I think we might start introducing our last presenter for this session. So we have Kaib Mohamed from the University Mehmed Bougara of Boumerdes, and he will present a contribution entitled Kernel Principal Component Analysis Improvement based on data reduction via class interval.
Hi and welcome everyone. I'm presenting kernel principal component analysis improvement based on data reduction via class interval. My presentation starts by giving objectives of this presentation, generalities about PCA and KPCA, RKPCA and the proposed approach, results, and finally conclusion. The objective of this study is to improve KPCA monitoring performance and reduce required storage space for the model and the execution time for the online phase of the monitoring system. Fault detection and diagnosis approach detects abnormalities within monitored system. There are two major categories of fault detection and diagnosis approach, which are model-based and data-driven. For large complex systems, it is more convenient to use data-driven methods rather than model-based. principal component analysis is widely used data-driven approach because of its flexibility. It is based on eigenvalue decomposition. PCA does assume that relationship between variables is linear. So automatically it will drop its reliability when it comes to nonlinear data sets. Kernel principal components analysis is an alternative solution to PCA's limitation. KPCA maps data from input space to a higher dimensional space via a mapping function. But the mapping function may be too hard to use, so we use kernel trick, which is use kernel function instead of the mapping function. The most used kernel function is the radial basis function. KPCA performs PCA in this higher dimensional space after the mapping. By performing the mapping from the input space to a higher dimensional space, data in this space use the eigen decomposition value will be higher. So it will take more storage space for the model, more execution time, and in some cases where the hardware is old or slow, KPCA may lose its ability for eigen decomposition. Reduced kernel PCA is based on KPCA algorithm. It only pre-processes data before applying conventional KPCA. Main idea is to select relevant observations from the training data set. RKPCA overcomes the problems related to the size of the data in the KPCA algorithm. This is the general training part of the reduced kernel principal component analysis, which is the same as kernel PCA. Only thing is that we have more step, which is reduced data. We start by collecting training data, then reduce data using a given technique, and then choose the kernel function, compute kernel matrix after normalizing data with unit variance, then center kernel matrix again, perform eigen decomposition, compute monitoring indices in the principal component subspace, residual subspace, and the combined index, and their limits. Confirm the model using testing data, and pass to the online monitoring. For the online monitoring part, we collect data, then normalize data using the mean and the standard deviation of the training data set, compute kernel matrix, center kernel matrix, compute monitoring indices, and check whether this monitoring indices exceeds its limit. If yes, the system is faulty and we acquire new data. If no, the system is healthy and we acquire new data. The proposed algorithm eliminates the least important information. It uses PCA as a filter to set apart important information and the least important one. The first residual component is used because it is the largest residual, which is the part of the least important information. Histogram is used to, which is class interval, is used to ensure that both original data set and reduced data set has the same distribution. Proposed algorithm performs PCA, then it selects the first residual score, which is TR, here mentioned TR, and PR is the first residual eigenvector. We compute the histogram of this vector, which is TR, then select the minimum appearance frequency in the histogram. For each bin, we compute the scaling of the appearance frequency in that bin over the minimum appearance frequency. Then select the corresponding, from each bin, select a number of observations, and from these observations, we select rows from the original data set. process overview, for this application, we have used Tennessee Eastman benchmark. Its data has 52 variables and 500 samples. For the faulty part, it has 21 faults. Each one has 960 samples. The faults occurs at sample number 160. The data is very useful for this study because it has both easy to detect faults and the ones that are quite challenging, like the third fault. This is the cost function used to select the appropriate reduced matrix and compare between different algorithms. It has the FIR value, which is related to the healthy part of the data, MDR values related to the faulty part, and DTD, it is the detection time delay. A1, A2, A3 are the weighting factors to focus on one monitoring indices if we want to. For this study, they are all one. This is the results obtained using the proposed algorithm. Beta is the number of bins in the histogram, and epsilon is the minimum appearance frequency. As we can see, for different bins, we have the same minimum appearance frequency, but that does not give us the same reduced matrix. They have the same size, but they are not the same. For the T-square monitoring indices, the one with 127 sample gives the best monitoring indices, monitoring performance. For the Q index, which is the residual subspace, the one with 252, number of pins 7, gives the best performance, and J, for the last column, gives the general performance. It is the mean of the three monitoring indices. This is used to select the appropriate reduced matrix to use generally for different monitoring indices at the same time. This is a comparison between the proposed method and different methods, kernel PCA and other reduced kernel PCA. For the T-square, which is the principal component subspace, KPCA and variogram RKPCA gives the best performance results, but the proposed algorithm are right next to them. The second, for the second monitoring indices Q, the proposed algorithm has the best performance. For the combined index, the KPCA algorithm and Euclidean distance RKPCA gives the best results. This is by how much we have enhanced the storage space and execution time. The storage space is directly related to the number of bins because the complexity of the storage space of the KPCA algorithm is n squared. And we can see that the proposed algorithm has reduced significantly the storage space and as well the execution time, which has n cube complexity, time complexity. The proposed, as conclusion, the proposed algorithm uses class interval technique to reduce the number of samples from the training data set. The proposed approach was applied to Tennessee Eastman process benchmark to prove its ability to detect faults based on different indices. The proposed approach was also compared to some of the existing approach that it has a decent performance and balanced between reducing the size of the data and maintaining good performance. Thanks for your attention.
Thanks for your presentation. Any questions from the audience? Please.
thank you for the presentation. I enjoyed it.
You're welcome.
I have a question. I'm curious about your selection for the weighting in your loss function. The weights in your loss function. The A1, A2, and A3, you said you selected them all as one, correct?
Yes.
Okay. I'm curious as to, is there a formal routine that you follow for selecting these weights, or how is the selection of these weights informed? Is it something that comes from previous literature, or is there some formal study or a well-accepted practice for selecting these, or are they subjective values that you decide on?
They are both subjective and previously used.
Okay.
The selection 111, so that we give all the monitoring metrics, FAR, MDR, and DTD, the same weight on the results.
Okay.
So if you want to, for example, concern more about MDR, you make A2 bigger than the other two.
Interesting. And out of curiosity, from, as you mentioned, it's from previously informed studies, is it typically 111, or are there certain instances where, from previous literature or from practice, there's more importance in the false alarm rate or the misdetections, or?
No, it's just a rule of thumb, 111.
So the rule of thumb is 111?
Yes,
okay.
111.
Thank you.
You're welcome.
Is there another question for this presentation? If no, I have one question. Thank you for this nice presentation. It's very interesting. In my think, when I use the PCA, principal complement analysis,
Yes.
for fault diagnosis, the data reduction is used by selecting the most relevant complement, the principal complement. This is why the data size is reduced.
Yes.
In your case, you don't talk about the principal complement, the choice of the principal complement, the projection. So I'm curious to know how the data are reduced without projecting in the part of the complement.
The data here is projected to the residual subspace. We have not used the principal component at all. Only the residual subspace, because it contains the not important information.
In the residual subspace,
yes,
all the variability is removed.
What?
So all the variability of the data is removed in the residual space.
Yes, but it can be considered as noise and etc.
In your method, the end goal is to detect and identify faults.
Yes, with reducing the size of the data set.
Okay, thank you.
You're welcome.
Is there some other questions?
Okay, so let's thank the speaker again. And prior to closing the session, let me thank you for attending and the organizers, and also Professor Jaziri for chairing with me the session. Okay. Thank you.
Welcome to the regular session of estimation and filtering methods for FTDI applications. I'm Chao Shang from Tsinghua University, and I'm glad to chair this session together with Professor Ping Zhang. So the first speaker is Mazzolelli Mirko from University of Bergamo. So welcome the first speaker.
Okay, so good afternoon. I'm Mazzoleni Mirko from University of Bergamo in Italy. First of all, let me recognize my colleagues, Roberto Sala, Fabiana Pirola, Fabio Previ from the same University of Bergamo, and especially my friend Pietro Boni, which is the main author of this talk. Okay, so what is the aim of this presentation? Our aim is to devise some indicators that are used to prioritize or sort causes of performance degradation of an industrial machinery. And we want to do this by relying on measured information that are symptoms of such performance degradation. So this is the outline of the presentation. We'll start with some context, motivation, and terminology. Then we will introduce our symptomatology indicators in both basic form and some simple extensions. And then we apply such computed indicators to shrink wrappers, to an industrial application. And then we'll draw some conclusions. So let's start with some context and motivation. As I just said, this work is motivated by an industrial collaboration with a manufacturing company that produces machinery for, let's say, the plastic sector. And in particular, we work with blow molding and shrink wrappers machinery. Now, these machines have a huge amount of alarms that arise in some faulty situations, the so-called alarms flooding. And however, not all these alarms are critical, not all are related to the current fault or unwanted state of the machine, and not all of these alarms impact the machine on its key performance indicator or indicators that in this talk for brevity we call them KPI. So there is a need to summarize the information to reach a quick decision about how to act when there is a fault or an unwanted state in our machinery. So again, the aim is to devise synthetic indicators that try to prioritize symptoms of KPI degradation in such machinery. An example of KPI that we will consider later will be the overall equipment effectiveness of the machine. So let's introduce some terminology. We define X as the set of variables of interest. They can be, for instance, machine alarms, but they can be other measurements that we collect. A small x is a specific variable of interest that might be a specific alarm code. Let's define I of x as the incidence that is a measure of a characteristics of the variable x, and can be a recurrence of an alarm, the time duration of such alarm, or a normalized absolute value of some measurement. We define theta KPI as a threshold for the KPI of a machinery, and if this performance indicator, that might be the effectiveness of the machine, goes below this threshold, this is an unwanted situation. Then we define I plus as the incidence of the variable x when the KPI is above its theta threshold, and I minus as the incidence of the variable of interest x when this KPI is below its threshold. Okay, so let's start with defining some symptomatology indicators. So given those incidences I plus and I minus for a set of variables x, we define the incidence rates of the variable x above and below the KPI threshold by simple ratios. That is, the incidence rate P plus is just the normalization of the incidences E plus over all the incidences for all the variables. And then we have the incidence rate P minus related to a variable X as the normalization of the incidence minus for the variable X with respect to all the other incidences of other variables. Now, what is the interpretation of these ratios? Basically, the larger P minus for a variable X is with respect to P plus for the same variable X, the more, let's say, eligible this variable X is as a symptom of a KPI decay below its threshold theta KPI. So this is the interpretation of these ratios. Now, we define a so-called prevalence indicator. We denote with the letter gamma. It depends on a variable X and obviously on a KPI threshold as the ratio of these indicators, P minus and P plus, for the same variable X. So what interpretation can we give to this prevalence indicator? We have that this gamma is equal to 0 when X affects the KPI only above the threshold. I say affect, but we can understand it as X is related to the KPI only above the threshold. Then we have this area when this ratio gamma is less than 1. If X affects or is related to the KPI more above than below the KPI threshold. Line when gamma is equal to 1 when X affects or is related to the KPI equally below and above its threshold. This area when gamma is greater than 1 when X affects the KPI more below than above its threshold. And then this line when gamma is equal to an infinity value if X affects the KPI only below its threshold. So this area, this red area here, is what we interpret as critical zone for KPI decay, because here we have variables that are more related or that are more present when the KPI is below its performance threshold theta KPI. So this is the interpretation that we give to this prevalence indicator. However, what we might observe is that two variables that are here denoted with this X and with this another X might have the same value of our indicator gamma. So in some way we lose, let's say, the magnitude of this indicator P minus. So the magnitude of how much each of the two variables affect the KPI below its threshold. So to try to quantify this, we introduce a second indicator, but basically it is the distance between each of this point below the line gamma x equal to 1, so the distance between each point to the line gamma x equal to 1. So this allows us to, let's say, to quantify the relevance of each variable x as a symptom of KPI degradation below the given threshold. Now, what might happen is that, again, this indicator might give, might assume the same value for two different variables. For instance, here, these distances dx2 and dx4 is basically the same. However, this first variable here intuitively affects more the KPI degradation because it is more present when the KPI is below its threshold. So again, these two indicators are a bit of complementary, and so we combine both of them into a single indicator delta, which again ranges from 0 to 1, and we call this as a symptomatology indicator for the variable of interest x. So this indicator delta is a single and aggregate indicator that measures how much a variable of interest x is symptomatic or it is related to a KPI degradation below a chosen threshold theta KPI. Okay, now this indicator that I just introduced, as you might observe, depends on the threshold theta. So different results happen when we change this threshold theta KPI. So the idea to evaluate better the variables more related to a KPI degradation is just to carry out the computation of this delta x for several thresholds that we set and combine the results. So in this way, we might define the indicator delta M that I call machine instance symptomatology indicator. So here the idea is that this indicator delta M that basically averages several indicator delta with respect to different threshold theta KPI is a generic indicator that is, first of all, theta independent, that is symptomatic of a KPI degradation for a specific monitored machinery M. So we try to be at most theta independent as possible. Now, this is of particular aid on the client user side of the machinery in our intuition. Indeed, the variables with the highest value of this indicator, delta M, are the ones to which the client, the user, must pay more attention and take care of to enhance the machine performance, so to avoid excessive KPI degradation. Now, if we consider to have at disposal a set M of several instances of the same machinery, it is possible to compute this indicator related to each machine, delta M, for each of those machines, and define an indicator for that type of machinery instead of limiting to a singular particular instance of that machine M. So, with the same rationale as before, we can average different indicators delta M with respect to different machines small m, and define this indicator, delta T, that I call machine type symptomatology indicator. And type means that we try to be at most independent of a particular instance of a specific type of machinery. This indicator, delta T, can be used to create a so-called symptomatology database, where the most relevant symptoms of a KPI degradation for that type of machinery are gathered. And in our idea, this can be of particular use to form the producer side, the producer that make that machine, that can analyze information about where to technically improve the design of that machinery to avoid such KPI degradation. So this is a summary. We have the indicator delta M, particular aid to the user, and gives indication of how or where to act to solve problems on a single machine instance. And then this indicator delta T, that can be of aid to the producer of the machinery to give him, her, indication on how, where to act to improve the machine type design. Now, we tested this on an industrial case study with real data applied to machines that are shrink wrappers. So basically, the aim of these shrink wrappers is to do packaging of a set of components. For instance, here we have some bottles that get separated to reach a certain specific number. Then we have a plastic sheet that is posed on this packaging, and then this plastic film has to be thermoretracted to make the packaging. So this is the process of the machine that we considered. These are some photos of these shrink wrappers, and such machines have a lot of alarms that we want to prioritize, sort out, to say, okay, these alarms are more important, causes more the KPI, or causes are more related to the KPI degradation. So again, the considered KPI in this application is the overall equipment effectiveness, OEE, that we call with the letter RS. For the shrink wrapper SW producer, a good efficiency is when this effectiveness is above or equal 95%. 94%. In application, we consider 4 different shrink wrappers of the same type, so 4 different instances of the same type of machine. As a variable of interest, x, we consider alarms that triggered a shrink wrapper to stop working. In the terminology, they are called stop reasons. They are basically alarms that cause the machine to stop. As incidence I of x, we consider the number of last consecutive appearances of that alarm x. So, to give some example, here we have a list of 14 stop reasons. For instance, the first one is anomaly at cardboard's enable zone. ID 2 is anomaly at cardboard's running zone, cardboard's reserve end, and so on. So a list of alarms that causes the machine to stop. As an example of the incident that is just discussed, that is the number of last consecutive appearances of the alarm X. Basically, this is an example. Here, in the first row, you have the overall effectiveness that we assume to degrade in some way. For instance, it starts 95, 90, 72, and then 49. And during this period, we have alarm number 1. Then the KPI rises again because there is no alarm with ID 0, 88, 95, 75, and then 51. And here we have alarm number 7, and so on. So last consecutive occurrences means basically that in this timestamp of the gathered data, we, even if we have 4 times number 1, we just consider the occurrences of the alarm 1 that I call I1, just to be of 1, because our idea is that the last occurrence is related to the less value of the KPI. And for instance, here we have 2 times alarm number 7, here and here, and we consider as the number of appearances of alarm number 7 to be just 2, because we have basically 2 strikes of alarm number 7. So this is the idea. Okay, and here the result of the indicator delta M that is related to a specific machine. Here we have 4 machines, SV1, 2, 3, and 4. We varied several threshold theta of the KPI. And as you can see, those 4 machines have their own peculiarities, their own specificities. For instance, for shrink wrapper 1, the most, say, important or stop reason related to KPI degradation is the alarm number 1 and 13. For the shrink wrapper 2, the most important alarm to KPI degradation is number 4, then we have 6. Here we have number 3, number 2, and here again number 6 and number 4. So each machine is basically a bit different from the other, even if they are the same type of machine. And to aggregate all of this, we compute the indicator delta T, that is that related to machine type, that gave us a priority, an ordering of which alarm is more related to a KPI degradation, in that case to the degradation of the effectiveness of the machine. Now, unfortunately, I don't have some quantitative comparison result, because the only way to assess this actually is to talk with the designers, with the engineer, with the users of this machine, and I can tell you that we talk with them and they say that these results are consistent with their expectations. So they were quite happy of this simple way, in the end, just summation and ratios, to try to have to sort out a list of a huge amount of alarms. So concluding, we devised a set of synthetic and I say also general indicators to help both users and producers of industrial machinery to rapidly assess problems on their machines. And I have to say that the importance of operators and designers, engineers, knowledge domain is still fundamental to interpret those indicators and take decisions. And the future research is devoted to extensively testing those indicators and use them for eventually predictive maintenance. Okay, thanks for your attention.
We have time for one quick question. Okay, I have one question. So you use ratios to define different indicators. Are there any normalization properties for these indicators?
Yes, actually, how these indicators are computed, they are computed to be between 0 and 1. So where 0 means low importance and 1 means maximum importance. I have to say sometimes that that might be anomalies in the computation. For instance, it may happen that this indicator here takes value infinity, and in this case we have to handle these instances separately.
Okay, thank you. Let's thank the speaker again. So the second speaker is Alan from University of Applied Science at Bingen.
All right. Thank you for giving me the opportunity to present my work. Today I will speak about fault diagnosis in protein exchange membrane fuel cells, where we conduct a performance assessment on 2 base filters. And this project is a cooperation between the University in Kaiserslautern and University of Applied Science in Bingen. And this work is supervised by Professor Michael Mangold and Professor Ping Chang. So a brief introduction onto our motivation is protein exchange membrane fuel cells, due to favorable characteristics, such as moderate operating temperatures, are emerged as a potential solution for electric powertrains. However, their durability is significantly limited due to harsh operating conditions and uncontrolled external environmental factors. Such operating conditions like start-stop or load cycling, which is defined by rapid transient load demands, and the environmental factors such as extreme temperatures and impurities. These can be traced to the faulty operating conditions of water management failures such as cell flooding and membrane drying, and also membrane cracking due to mechanical and chemical stresses, and catalytic degradation. But in our work, we only consider cell flooding and catalytic degradation, and we do that due to the significance of the faults. Since 50% of all PEM fuel cell faults are caused by water management failures. In addition, the catalyst layers are platinum-based, which are rare material and increases the fuel cell manufacturing costs. And this leads us to our problem statements, where due to the compact design of fuel cells, in situ measurements is infeasible. Therefore, we try to estimate internal cell parameters to be used as fault indicators for our fault diagnosis system. So our workflow is we first develop a diagnostic-oriented PEM fuel cell catalytic degradation model, a multi-scale degradation model. And the main objective of this model is that due to scarcity of data of catalytic degradation, we wanted to simulate data that can be used to assess our fault diagnosis system. And then at the second part, we develop a multiple model fault diagnosis system, which is, I believe, introduced by Shalom in 2001. And this entails 2 tasks. First, we develop our fault models, and then we determine our model selection method, which is based on the Bayes rule. And then we implement our state estimation algorithms. In our case, we adopt 2 Bayes filters, the square root unscented Kalman filter and the particle filter. And then finally, our results, which is composed of 2 parts, where we simulate the results of our proposed diagnosis scheme, and then we conduct a performance assessment of both base filters within our multiple model fault diagnosis scheme. And almost less than a year ago, we started to construct our test bench, which is funded by the Ministry of Education and Research in Germany. And it's a full hydrogen system where we have a PEM electrolyzer, metal hydride hydrogen storage, and this feeds into a dead-end PEM fuel cell. And our system controllables for now is the cell current, so what the current we draw from the fuel cell or our load, and the upstream pressure of hydrogen in the fuel cell, and the flow rate of hydrogen from the PEM electrolyzer. So first, I would like to talk about the PEM fuel cell degradation model without going too much into detail. But again, the main idea of the degradation model was to somehow have a qualitative representation of the molecular effects, and we can couple it into the global stack performance. So as we can see, the multi-scale model is a 5-state model, and it's a multiple input, multiple output nonlinear system where we have the inputs of the cell current, the volumetric inlet airflow rate, and the molar concentration of oxygen in the inlet air. And our two measurement is right here is the molar concentration of oxygen and the cell voltage. So at first I would talk about the microscopic scale, which is mainly consists of the mass conservation principles and the reaction rate of oxygen. And our 3 states is the molar concentration of oxygen in the flow channels and the catalyst layer, and our activation losses, which is just a capacitance effect to initiate electrochemical reactions. And these are the equations of the model. What I would like to talk about here is the coupling term Kc. So this coupling term is what propagates the molecular effects of catalytic degradation into our microscopic scale. And how we calculate Kc is by assuming that the catalytic degradation is only driven by the platinum dissolution. So first, the catalyst layer is manufactured by finely distributed carbon-supported platinum particles. And under undesired operating conditions, the platinum particles are prone to degradation. And this model is motivated by Darling and Mears, which they develop a lumped model for platinum dissolution through the characterized by these by 2 electrochemical reactions from platinum dissolution, platinum oxide, the platinum oxide formation, and the chemical dissolution of platinum oxide. And using these electrochemical reactions, we have the two states: the fraction of platinum oxide coverage, which is the coverage of an oxide layer on the platinum particle, and our particle radius. And here is our equations. Just 2 comments. The first one is we only consider the forward reaction rate of platinum dissolution. So we assume a worst case degradation scenario. This means that all the dissoluted platinum is somehow lost. We don't assume that we don't consider that platinum can be plated again. And finally, that the potential difference that initiates the electrochemical reaction is computed by the interfacial potential difference between on the cathodic electrode. And so the big part of the multiple model fault diagnosis is to develop the fault models. And so how we do that is the multiple models are distinguished by an additional system state. And this system state is specifically a system parameter that is defined by the effects or the failure effects of the corresponding fault. And this parameter is then augmented to our system state vector described as a stationary process and is jointly estimated by the base filters. So if we look into it in more detail, let's say we look at the flooding model and we revisit the equations of our macroscopic model. So flooding is defined as the accumulation of liquid water in the electrode, blocking the diffusion or the microporous structure of the gas diffusion layer. So what happens is if we look at X1 and X2 and say this is the molar concentrations of oxygen, and if we reduce this beta, then we increase the mass transportation resistance. So what happens is if we look at the green color parameter beta here, we substitute it with beta, and then we describe it as a stationary process. And this will be jointly estimated by the base filter. Similarly, with catalytic degradation, we introduce a new parameter that is decoupling the product of Kc and IC note. And IC note is a catalytic quality parameter which can be used or can be thought as of the state of health of the catalyst layer. And this product is the zeta CD. And if we take this the product here and we substitute with our fourth state, and then similarly we described it as a state with zero dynamics. So here we have two models, a flooding model and a catalytic degradation model, and each with a unique or a different system parameter to be estimated. And so if we sum it up, this is the full diagnosed system schematic. So the fuel cell model, which is the multi-scale model, will be thought of as our plant. And we introduce the failure effects of catalytic degradation through Kc, which is propagated by the microscopic model, and beta F. So we introduce flooding by manipulating this parameter beta to decrease the interlayer mass transportation. And as we can see, both of them are considered as multiplicative faults. And running in parallel are the three models. The first is the normal model, which is a benchmark of a fault-free model. The second is our flooding model with our additional state beta. And the third is the degradation model. And we implement our base filters, which provides the estimates of the system state conditioned by the model assumption and the parameters estimated. And also using the innovation sequence and the output error covariance, we are able to construct a prior belief using a Gaussian density function that the likelihood of the measurement yk conditioned by the ith model. And this information is propagated to the base rule model selection method. And this is here where we actually generate our fault indication signals. And the fault indication signals are only the probability that the given model or the ith model is true given the current measurement. And then we derive a decision logic for the fault indication signals, and then if all works fine, we have knowledge on the fault or the current operating system regime. So the first plots, I would just like to show the effects of each failure. So these are the two measurements, our molar concentration of oxygen in the catalyst layer and the cell voltage. And we can see that due to flooding or due to the manipulation of beta, we have a decrease in the molar concentration. And also we can see a continuous degradation of the cell voltage due to catalytic degradation. On the right side, we see the estimates provided by the Kalman filter and the particle filter. And there is also a plant model mismatch since the estimates are provided based on the fault-free model. And it's interesting to look here because looking at the difference between the true system states and the normal, we can actually see the effects of each failure on the internal system dynamics. And then the second part of our results is the parameter estimation that that is provided by each model. So the top plot here is the estimation provided by both base filters of beta that is considered in the flooding model, and the zeta CD in the catalytic degradation model. And the black line here is the true system value, and we can see that between 400 and 700 seconds, we manipulated the beta to impose or induce the flooding effects. And as we can also interestingly that at idle conditions, both base filters are not able to see or to estimate the system value, since there is no electrochemical reactions and there's no mass transportation occurring in the fuel cell. And both of them have a similar estimation performance. And if we look at the zeta CD, which we can see the degradation of the catalytic quality of the catalyst layer, and we can see that the particle filter is sensitive to the input of the change in beta. And then in the second part, on your left-hand side is the full diagnosis of flooding and catalytic degradation. And the top plot is the results of the Kalman filter, and the bottom plot is on a particle filter. And for the first 100 seconds, the fuel cell is idle, and all three models share a similar probability. And as soon as the current is introduced, electrochemical reactions are initiated, and we can see that the degradation model gains the highest probability. And in addition, during flooding, both base filters exhibit similar performance in detection of flooding. And again, as soon as, let's say, flooding was treated by purging, we can see that the degradation model gains the highest probability, indicating the faulty operating condition of catalytic degradation. So these are some performance criteria of between the Kalman filter and the particle filter. I would just want to comment on the computational time. Since we simulated this on MATLAB, the models were computed in series. But in reality, we can do that in parallel, which would decrease the computational time. However, the Kalman filter would still provide superiority in the computational time. Finally, the conclusion is that we would like to take that the cell voltage and molar concentrations of oxygen can be used as health indicators for detection of flooding and degradation. The square root unscented Kalman filter is superior to particle filter when implemented in a multiple model full diagnosed scheme, since the particle filter is based on a Monte Carlo simulation, and we have almost 200 particles we have to propagate through the nonlinear system for 3 models. And then another interesting point was the estimation of the mass transfer coefficient, which is attributed to the flooding model, can only be detected when a minimum current is imposed on the fuel cell. And thank you.
So we have a short time for one question. So I have a question. So I think this is a very interesting work. So can your method handle the situation with some unseen out-of-sample faults? So what will we obtain for two-state estimation algorithms? So what will we obtain if we are facing some newly unseen out-of-sample faults that we do not consider in your algorithm design?
So the multiple model, it has to be a predefined fault that you assume in your multiple model fault diagnosis scheme. However, for example, in our catalytic degradation model, we didn't include the microscopic model. So because the degradation is a complex mechanism, and this means by discarding the microscopic model, we can claim that the diagnosis scheme can detect all degradation for let's say, mechanisms or causes successfully. Yeah.
Okay, thank you. Let's thank the second speaker again. So the third speaker is from Aix-Marseille University, and the topic is about the hydrogen rate prediction in natural gas pipelines, supplying industrial machines in the frame of power to gas technology.
So, good afternoon all. Happy to share with you in this presentation our research work entitled Hydrogen Rate Prediction in Natural Gas Pipes Supplying Industrial Machines in the Frame of Port-to-Gas Technology. This work is realized at the Institute of Materials, Microsystems and Nanotechnologies of Provence at Aix-Marseille University in France, at the team Sensors and Instrumentation. I will start by an introduction. I will give you a quick description of the sensor design. The sensor is designed in our team, Sensors and Instrumentation. The experimental setup used for sensor characterization. The prediction algorithm implemented in 3 steps, results and discussion, and I will finish by a conclusion. The principle of port-to-gas technology is to convert the excess of renewable energy produced by photovoltaic systems and wind turbines into a hydrogen. This later is injected in the pipes supplying natural gas. This mixture, natural gas, hydrogen, will supply power some machines and turbines that can operate using this mixture. Here in this scheme, you have an overview of the French port-to-gas demonstrator called Jupiter. However, controlling the hydrogen concentrations in the mixture hydrogen-natural gas is challenging because machines and turbines designed for natural gas operation have specific hydrogen rate limits and cannot accommodate significant variations in the mixture. Therefore, forecasting the time evolution of the hydrogen rate in the mixture with a sufficiently long forecasting horizon is necessary. It is essential. This is why we proposed this work, this paper, with a data-driven solution that combines a new hydrogen sensor with a geometric prediction models for forecasting the hydrogen rate in the mixture hydrogen, natural gas in the frame of port-to-gas technology in anaerobic environment. Sensor description. The first hydrogen sensor developed in our team is a palladium-based thin film resistive sensor that enables hydrogen detection by reversibly decomposing and adsorbing hydrogen in its surface. However, this first version of the sensor has a limit, an issue, where the hydrogen adsorption expands the palladium crystal lattice, causing hysteresis in the sensor. To overcome this issue, a gold thin film is added to the palladium thin film. This allow the sensor to slightly increase the latest structure, reducing thus the energy barrier induced by strain upon hydrogen adsorption and minimize the hysteresis. Here you have an overview of the 3 steps of the design of this microsensor. As I'm not an expert on the microsensor's design, if you need more information and details about the reaction between the hydrogen and the thin film of palladium gold to affect and to generate, to vary the resistance of the thin film, you can ask our colleagues and co-authors, Jean-Luc Séguin and Thomas Fioridou, or I invite you to read the following paper, Sensor for Anaerobic Hydrogen Measurement, comparative study between the resistive palladium gold based sensor and a commercial thermal conductivity sensor. Experimental setup. The experimental test bench used for the sensor characterization is given in the following picture. It is available in EM-Design experimental test bench systems. It is constituted of 2 main parts. A dilution systems, whose inputs are the hydrogen and the natural gas. The mixture is created in the dilution systems and controlled by a regulator. Then the created mixture is injected to the test chamber involving the sensor, and a source meter allows the measurement of 2 variables, 2 resistances. The resistance R0, which is the value of the sensor stable baseline resistance under constant temperature and pure natural gas flow. The resistance R, which is the value of the sensor's electrical resistance under hydrogen exposure. These 2 measurements are used to calculate the sensor response using the following equation. Then, to establish the relation between the hydrogen rate and the sensor response, the following table is built and it is used to identify a regression model. Among the models that we are implemented and tested, the model giving the most interesting performance is an autoregressive model with an exogenous input. Powerful and easy to implement. It is given in the following equation, where Y is the hydrogen rate and X is the sensor response. For forecasting the hydrogen rate evolution in the mixture hydrogen natural gas, a prediction algorithm is implemented in 3 steps. The first step is the detection of the direction change in the hydrogen rate. In fact, the hydrogen rate in the mixture hydrogen natural gas can have 3 states: a stabilized state, an increasing, or a decreasing. And to transit from one state to another, the rate change direction. This change is detected by a colored trend index. It is expressed in the following equation. I have some typos in this equation. In the following equation, where alpha, is missing here, alpha, is a percentage that describes the velocity variation over time. TS is the observation window of time, predefined, and v is the velocity of progress of the hydrogen rate at time e. This velocity is expressed and defined as follows. It is considered as the numerical differentiation derivative of the distance variable d according to the predefined observation window. It's expressed as follows, where d is the hydrogen rate value at time t. It is exactly the difference between the critical threshold and the actual value of the hydrogen rate. V is the hydrogen rate velocity at time t. And Ts is a predefined time windows. Knowing the velocity and the distance, it is possible to estimate the remaining time before reaching critical threshold, RT-CT. It relies on both distance and the speed, and it is expressed by the ratio, by the quotient of the distance and the speed as follows. The principle of the RT-CT calculation is the same as the principle of the geolocalization systems. If we know the starting point and the end point, and we know the velocity of progress from the starting point to the end point, it is possible to estimate the remaining time before reaching the end point. This is the principle of these geometric models. Then, the knowledge of the remaining time before reaching critical thresholds allows the end user of the mixture hydrogen natural gas to anticipate the evolution of this mixture, of the hydrogen rate in this mixture, and to correct this rate at his level and avoid machines shutdowns. Results and discussion. This first figure shows in the up figure the evolution of the hydrogen rate, the three stages, stabilized stage, increasing and decreasing. And we can see that the rate increases between t equal 1 minute and t equal 18 minutes. Then it decreases between t equal 18 minutes and t equal 40 minutes. We can see that at t equal 18 minutes, the sense change. I missed to say that the detection index, the trend index, have three states. 0, when it is stabilized, -1, when it decreases, and 1, when it increases. Here also, we have an uncertainty neglected less than 1 minute at time t equal 14 minutes. In the following figures, we have the time evolution of the distance and the speed in the increasing phase of the hydrogen rate. The distance between the current rate and the upper critical threshold is constant between t equal 2 minutes and t equal 3.7 minutes, for example, which means that the rate is stable. Then, between t equal 3.7 minutes and t equal 4.2 minutes, the distance increases between the current rate and the maximum threshold, which means that the rate increases. This figure shows also the high sensitivity of this algorithm to a small change in the hydrogen rate. Here you can see the time evolution of the remaining time before reaching the critical threshold. This figure shows that it remains constant when the hydrogen rate stabilizes and decreases following the rate of variation of the hydrogen rate. For example, at time t equal 8 minutes, here, the remaining time before reaching critical threshold is about 16 minutes. 16 minutes, which is long enough for the user, the end user, to correct the hydrogen rate in the mixture and avoid unplanned shutdowns of his machine or turbine. In conclusion, this study presents a method for estimating and predicting the hydrogen rate in the hydrogen natural gas mixture in the frame of power-to-gas technology in anaerobic environment without presence of oxygen. The experimental tests demonstrate that the sensor is able to accurately detect hydrogen gas in anaerobic environment across a wide concentration range. This sensor exhibits consistent and repeatable measurement throughout the entire exposure range. The geometric algorithm implemented for the prediction using sensors' experimental data yields a high satisfactory result. As future works, we can explore the scalability and the applicability of this method in a real-world environment. Thank you for your attention.
Any questions?
Question. Thank you very much for the talk. How about the accuracy of the prediction you have got? So is there some validation about the predicted values?
Thank you for this interesting question. In this work, we are not evaluating the accuracy of this method with precision, but its accuracy is more than 90% when the data are not noisy.
Any questions? Okay, I have a question. So I'm interested in the ARX modeling you have used to build a prediction model. So when we deal with practical data, we need to handle the bias term in the ARX model. So how do you estimate the bias, the constant bias? So is it by first normalizing the input and output variables, or by treating it as a free parameter in the ARX model?
The parameters of the RX model are identified using an easy and a known identification method. We used the last square method, recursive last square method.
Okay, thank you. Let's thank the speaker again. So, okay, my job has been done. So next, the session will be chaired by Professor Zhang.
Yeah, so the fourth speaker, seems that we don't see the fourth speaker until now, and there's also no video that has been uploaded. So we have to wait for 20 minutes, and we will continue at 17 o'clock 35. So thank you and see you later. Our session, and the next speaker is Chao Shang from Tsinghua University, and he will talk about fast trend extraction based on deep directional LSTM network.
Okay, thanks for the introduction. So I'm Chao Shang from Tsinghua University. Today I'm glad to introduce our work and on behalf of my student. So this is outline. So actually, data trend is a reflection of the changing characteristic of time series data. So actually, it is a symbolic information. And this is exactly how human understands time series. For example, so if we take a look at the data from a process variable, so it is clear that this variable stays constant, reaches a steady condition, and then drops, and then fluctuates, and then drops again until it reaches a steady operation again. So actually, such information can help us in a number of tasks, especially in some knowledge-informed applications such as system identification, process monitoring, and fault diagnosis. So even if trend extraction may seem very simple for human beings, it is not so easy in algorithm design. So actually, for trend extraction, we need to perform data segmentation. So this involves identification of several change points in a time series data as shown here. So actually, we need to first segment the entire time series into different segments and then fit each segment using a low complexity expression, for example, the primitives of the trends. So in this way, we can interpret the changes with the time series data in an interpretable way. But the major challenges lies in the determination of the change points, which is a combinatorial optimization problem. So current endeavors in trend extraction algorithms can be classified into two streams. The first stream is based on global optimization. So by defining a cost based on the residual and some penalty functions, we can make a trade-off between the data fitting and the complexity. Another stream is based on statistical tests. Actually, we decide the configuration of change points iteratively through some statistical tests. But both lines of methods have some deficiencies. So actually, the success of both methods heavily relies on the selection of hyperparameters. Meanwhile, the statistical tests are typically performed in a bottom-up fashion, so it inevitably suffers from suboptimality. Even though the global optimization methods shows better performance, they suffer from heavy computations. So mathematically speaking, we can formulate the global optimization-based methods as follows. So by first splitting the entire time series data into different sections and then perform polynomial fitting of segmented time series data, we can obtain the underlying trend and of the time series data, and also this helps us to filter the noise. So the decision variables include the coefficients of the polynomials as well as all the change points. So the cost function can be defined as a total fitting error given the number of the data segments. Of course, we can add some constraints to ensure the monotonicity of each segment as well as continuity. So by minimizing this cost function over all polynomial coefficients and the configuration of the changing points, we can obtain in some sense the optimal trend extraction result. So to efficiently solve this problem, the dynamic programming gives us a viable solution. So even if it is not an NP-hard problem, it still suffers from a cubic computational complexity. So this is very demanding in online use. So meanwhile, another important issue is how to decide the number of segments within the time series data. So there are various criteria in literature, for example, the two-sided criterion for choosing M, and other information theoretical criteria. However, the success mainly relies on the human choice, and this known methods has no tuning freedom. So we seek to address these challenges by providing new end-to-end learning scheme. So our main idea is to use deep neural network to learn a direct mapping from the original time series data to the underlying trend. So it has two phases, namely the offline training and online inference. So in the offline phase, we use dynamic programming-based algorithm, which may be slow, to extract some data trend and then construct a training data set. Using this data set, we can train a neural network offline, which can be further used in the online inference phase to extract the trend of the input data very fastly. So this is a schematic of the offline training phase. So after collecting some industrial process data, we run the dynamic programming algorithm on that data, where the number of segments, data segments, is tuned by a human expert. So after collecting the data, original data and the estimated trends, we use them as a training data set to train a neural network to predict the underlying trend of the original the data. In this way, the knowledge, the expert knowledge can be efficiently encoded in the neural network structure. So for the structure, we use a deep bidirectional LSTM model. So why do we use this one? This is because the underlying trend is related to both past and future data, so the generic LSTM model is not necessary. Meanwhile, we also integrate convolutions and attention mechanism into a network structure. So for the bidirectional LSTM, we impose some deep connections to make it more powerful in handling long sequence data. And we also incorporate the attention mechanism, which has been proven very efficient in tackling long sequences, especially in large language models, to improve the performance in training extraction. Meanwhile, we also propose a novel regularizer for training neural networks, which is tailored to our trend extraction tasks. The idea is that for trend extraction, the smoothness of the prediction in the neural network is also very important, in addition to the total fitting error. So in the loss function we consider, we impose an additional regularizer in addition to the traditional fitting error, such as the mean square error. So here we use a temporal difference as a measure of smoothness to encourage the smoothness of the prediction of the neural networks. Here the C is the tunable trade-off parameters that can be adjusted by the user. So Next, we see some examples. So here we use a real process data from a flow control loop in a plant in China. So the entire data set is has a very large size, and we use this data set to train the model and then validate the performance. So we first perform some ablation studies. That is because our neural network has a number of ingredients. We remove some of their ingredients and look at their performance. We can see that our method can well capture the data trend by using the offline neural network training, even if this data set contains very heavy noise. Meanwhile, all the ingredients, including the convolutions, bidirectional collection, deep structure, and attention mechanisms, help to improve the performance, because both the fitting error and the smoothness get improved if we include more ingredients into the neural network structure. By taking a closer look at some snapshots, so we can see that our proposed method performs the best and closest to the oracle, that means the human expert. Then we investigate the effect of the new regularizer. So actually the regularizer seeks to balance between the fitting error and the smoothness. So if we choose this value of C, the regularization parameter larger, we can see that the smoothness gets improved at a cost of a larger fitting error. So this provides an effective way to further encourage the smoothness of the neural network. Finally, we investigate the computational cost. We train the neural network using an NVIDIA GeForce GPU and then make online inference. So we can see that for traditional dynamic programming algorithm, it takes more than 1 hour to extract the underlying trend, which is rather costly. So our method takes some time for offline network training. For example, when we consider a more complicated structure, we need more training time. But this is acceptable because in offline phase, we do not have such a critical time requirement. But the advantage is that the online inference is quite fast. It only takes a few seconds, which is much faster than directly solving a dynamical programming problem. So this can give us a very efficient online implementation. So let me make the conclusion. So in this work, we proposed a practical end-to-end learning approach to online data trend extraction. It has 2 stages. The first is offline neural network training, and the second is online inference. By choosing the hyperparameters from a human expert, the expert knowledge can be further incorporated into the neural network. And by utilizing the convolutions, attention mechanism, and bidirectional connections, a good capturing of data trend can be benefited. And most importantly, the computational cost can be significantly reduced. And it can well mimic the oracle given by the expert and can be useful in some online tasks such as fault diagnosis. Okay, thank you for your attention. Your questions and comments are warmly welcome.
Yeah, thank you very much for the nice talk. If there are some questions. So maybe I will start with some questions. So here I must say that at first, the whole time before you begin to talk, I have misunderstood the title. I have thought that you want to extract fast trend, but you mean that it's a fast approach to extract indeed slow trend, right?
Yeah.
So one question. So in the neural network, so what are the inputs? So finally, to the neural network, or the current data and the past data?
Okay, this is a very interesting question. So actually, we use recurrent neural networks that can seamlessly use a time series data as its inputs. So the input is a sequence, and the output is also a sequence. Both of them have the same length.
So the question is, you don't want to extract the trend online, or you want to extract the trend online. So if you do it online, so you will use then the past data at that time that is available.
Yeah, that's correct. We use a neural network in a batch form. Actually, when a batch of data needs to be filtered, or we seek to extract its trend, we make inference use a neural network.
So batch data, you mean that you just put one batch of data, do some analysis, do the next batch?
Yeah, so I think this is problem dependent. For example, in fault diagnosis tasks, we need to got some symbolic representations of the underlying trends and then make a diagnostic decision. So actually, this may not be executed in every time instance, but rather in a batch form.
Okay, thank you. And I have also another question. The neural network, finally, so you have compared different kinds of neural networks, and finally the neural network, so how is your experience, how complex or the structure of the best type in your opinion at the end? So how about the complexity?
So you mean the complexity of the neural network?
Yes.
So actually, the input size and output size are set as 15. So I think it's a moderate size of the RNN. And we set the depth of the bidirectional LSTM is 3. So it's a little bit deep, but it's much shallower than those used in computer vision and other machine learning tasks.
Okay, so thank you very much. So is there some other question? Okay, so it doesn't seem to be this case. Then let's thank the speaker again.
Thank you.
So now we will go to the next talk. It's also the last talk in this session. This presentation will be given by Augustin Alonso from GIPSA Lab in France, located in Grenoble.
Okay, welcome to this presentation about model-based head losses estimation for hydropower plants. My name is Augustin Alonso. I'm a PhD student working for EDF, a French electric utility company, in an engineering center dedicated to hydropower plants. My research work is supervised by Gérard Robert and Gildas Besançon. Here is a quick summary of my presentation. We start with the context before developing an hydraulic state space model. I will next introduce sensors and raise the subject of model reduction and noise filtering. Different parameter identification approaches will be presented and compared thanks to industrial data. An hydropower plant uses falling water to produce electricity. Here you can see a layout of a typical hydropower plant. In this article, we will focus our attention on water transportation between the upstream reservoir and the turbine. The objective of this article is to find a way to monitor hydropower plants, especially the evolution of head losses because of its incidence on power plant efficiency. We want to maximize the hydraulic power supplies to the turbines by maintaining head losses as low as possible. So we do that using data from sensors and accurate physical model and identification algorithm such as ordinary least squares or extended Kalman filter to estimate some physical parameters. We encounter some obstacles presented here. Data are produced by physical sensors installed in a real hydropower plant. We have to deal with measurement noise, low sampling rate, and quantization effects. A very important part of our model-based approach is to develop an accurate model representative to the process, but not too complicated because it must be interpretable. Finally, we try to compare some estimation algorithm among an impressive number of methods available in the literature. Let's start with the hydraulic model development. As I said before, we focus our attention on water transportation between the upstream reservoir and the power plant. The water stored in the upstream reservoir flows through a low-pressure tunnel, which is here, which is almost horizontal. The tunnel is usually followed by a safety system designed to absorb and dampen strong pressure variation called the surge tank. The water continues to flow through a high-pressure pipe called penstock. At the power plant inlet, the penstock can be split into several pipes to supply turbines. The physical theory we used is the generalized Bernoulli principle, which is valid along a streamline used here for the example between points 1 and 2. In this equation, we can already identify three physical quantities involved: elevation, water pressure, and flow rate. Some parameters are already known as water density, cross-sectional area, or length of pipes. But the unknown parameter we want to know is the head loss coefficient K. This friction term is important because it gives us an indication of the state of health of the pipe and power plant efficiency. We apply this principle between points B and E, passing through point C. Then between point E and F, passing through point C and R. We add a surge tank model that relates water level and flow rate. We then obtain a three-state space model which involves three parameters to estimate. Ka as a regular head loss coefficient in tunnel, Ke as singular head loss coefficient in surge tank's diaphragm, and Kc as regular head loss coefficient in penstock. In this section, I will introduce you to the sensor we use for our work. In the model inputs data, we have an upstream reservoir level sensor and a pressure sensor located in one of the branches feeding the power plant. At certain operating points, this sensor is affected by hydraulic disturbances generated by the downstream turbine. In our case, two of the three model states are measured: the flow rate in the penstock and the water level in the surge tank. However, this level sensor is not always installed depending on the plant configuration. When a hydropower plant shuts down, the level and pressure sensor shown in the legend converge, are supposed to converge on the same value. In practice, this is not really the case, since the sensors are not properly calibrated, which means they are biased. One approach we can explore is to add this bias to the model and try to estimate them. So far, we have 3 inputs, 3 states, and 5 parameters now to estimate. 3 head losses parameters and 2 sensor bias. Under these conditions, the model is not observable. If the model is too complex, we will perform a model reduction, and if the data are too noisy, we will filter them. This is what I will present now. Answering we have only small transients, we can simplify the model as follows by removing the yellow part. At steady state, the simplification is even more significant, as you see. A DCT filter can be used, for example, or we can remove disturbances and large transients based on the signal variance threshold. The hydraulic model is now observable since we have to identify 2 parameters and 2 bias sensors. I'm going to present the identification algorithm we've tried. In the best case, the search tank water level is known. The first approach consists in identifying the 4 parameters using ordinary least squares as specified here. Using the second derivative of the measured data requires the use of a filter on this data. A second approach is to use ordinary least squares on the steady state model. As you see, if the search tank level is not known, we have to estimate only 3 parameters, and we can't use the previous approaches. So we used an extended Kalman filter to estimate the parameter using the well-known state augmentation trick you can see here. And as a final approach, we called the mixed approach. It consists of estimate 2 parameters first, including the global head loss coefficient KT with ordinary least squares, and then to distinguish head loss coefficient Ka and Kc using an extended Kalman filter. The last part is dedicated to a comparison of the approach explored. An initial simulation validation was carried to obtain several performance indicators. The result is here. We have several indicators. We can observe that the water level in the when the water level is known here. The best approach is probably the ordinary least squares here. Whereas the case of unknown water level in search tank, the mixed approach here seems to be better, except from the global head loss coefficient, KT. We will now compare the approaches for real data collected in a medium-sized power plant in the French Alps. We can now only compare estimated parameters since we don't know their real value. And we see here the negative value found by extended Kalman filter. This parameter is not a real parameter, so we prefer use a mixed approach in this case. And here you can see we can compare the reconstructed states in red with the measured states in green. The results are quite interesting. The model is quite accurate. In conclusion, we sought to maximize power plant efficiency and determine some default in water. We have to estimate some physical parameters, such as head loss coefficients. And hydraulic models are developed for this objective, and some parameter identification approach are proposed. They are compared using industrial data collected from a real power plant. And for the next purpose, we can try to explore other algorithms such as adaptive Kalman filter, smooth Kalman filter, and scented Kalman filter. Thanks for your attention.
Yeah, thank you very much for the nice talk. Is there some question? Please.
Thanks for your presentation. How do you validate the source time level?
Validate what?
The source time level. You say you are estimating the source time level, the level of the... How do you measure this in real...
For the power plant we selected, this value is measured by a sensor. Here. This is what you...
Yes, because you... okay, I saw. So you have some pressure sensor like this. So why do you need to estimate this if you have this pressure sensor?
Because many power plants don't have sensor for this state, but we have selected this power plant to evaluate the
because I suppose for a power plant is to buy a pressure sensor is not expensive.
And if we don't have, it's more difficult to evaluate the performance of the algorithm.
Okay, thank you.
Some other question? Okay, so I have some question. So head loss, does it mean the pressure loss or the head loss?
What do you mean?
The head loss.
The head loss.
Yeah, what's the physical meaning of head loss? Is the
head loss is a friction term.
Friction term. Okay, okay, thank you. So you have some states in the system model. So what are the physical minutes of the states used in your model? The physical minutes of the states in your model.
This slide?
Yes. Okay, so the flow rate or yeah.
Yes, the flow rate. You want to explain what term?
So QA, QC, ZE. So what are the physical meaning of it?
Yes.
Yeah.
Flow rate. It's explained.
I think Q is clear. So what is the Z? Okay.
It's a flow rate. Yes.
Flow rate. Okay. Okay. Thank you. Yeah. So maybe to the last second page before conclusion the page.
Yes. This slide?
Yes. So it seems that the sensor looks a little more smooth than the simulator in the figure in the middle. So why the simulator have even more fluctuations than the sensor measurements?
It's because of the input data of the model. The pressure sensor is very disturbing. As you saw here. Sorry. Here. This is the input of the model, and it's very disturbing.
Yes, I understand. Thank you. So is there some other question? Okay, if not, then we thank the speaker again. And we would also like to thank all the speakers and all the audience for your attention. So wish you a nice evening, nice dinner.